Hello there, and welcome to the Sleepy Science channel. Tonight we will be exploring one of the most fundamental forces that shapes our entire experience of the world: light. It surrounds us every moment. It reveals colors we never stop to question, and it carries secrets about the nature of reality itself. From the warm glow of a candle to the brilliant arc of a rainbow, from the shimmering aurora in polar skies to the invisible waves that warm our skin, light is everywhere. And yet, most of us have never stopped to truly understand what it is. Tonight, we will journey through the physics of light and color in a way that is gentle, calming, and filled with wonder. If you enjoy these quiet explorations of science, I invite you to like and subscribe, or share a thought down in the comments. It helps others discover this peaceful corner of learning, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and let the glow of knowledge carry you softly into the night. Let's begin. Light is both a wave and a particle at the same time. For centuries, scientists debated the true nature of light. Some believed it traveled as waves, rippling through space, like sound through air. Others argued it must be made of tiny particles, little bullets of energy shooting forward. The truth turned out to be stranger than either side imagined. Light is both. It behaves as a wave when it bends around corners, creates patterns of interference, and spreads across space. But it also acts as a particle when it strikes surfaces, transfers energy in discrete packets, and interacts with atoms. These packets are called photons. Each one carries a specific amount of energy, determined by the color of the light it represents. This dual nature is not a flaw in our understanding. It is a fundamental truth about reality. Light exists in a way that does not fit neatly into our everyday experience. It is a reminder that the universe operates by rules that are elegant, mysterious, and sometimes beyond simple explanation. When you see light streaming through a window, you are witnessing this duality in action. Waves and particles, inseparable, dancing together. Light travels faster than anything else in the universe. Nothing moves faster than light. In the vacuum of empty space, light travels at exactly 299,792,458 meters per second. That is roughly 300 million meters every single second, fast enough to circle the entire Earth more than 7 times in just 1 second. This speed is not just impressive, it is the cosmic speed limit, the ultimate barrier that nothing with mass can ever cross. Einstein's theory of relativity tells us that as objects approach the speed of light, time itself begins to slow down for them, and their mass increases toward infinity. Light itself moves at this speed because photons have no mass at all. They are pure energy racing through the void. This speed defines how we see the universe. The light from the sun takes about 8 minutes to reach us. The light from distant stars takes years, centuries, or even billions of years. When you look up at the night sky, you are not seeing the present, you are seeing the past, carried to you at the fastest speed nature allows. White light is actually made of every color combined. When sunlight pours through your window, it looks colorless, clean, and pure. But appearances can be deceiving. White light is not a single thing. It is a blend of all the colors of the visible spectrum mixed together: red, orange, yellow, green, blue, indigo, and violet, all flowing together in harmony. This was first demonstrated by Isaac Newton in 1666. He used a glass prism to split a beam of sunlight and watched as it spread into a beautiful rainbow of colors on the wall. Then, using a second prism, he recombined those colors back into white light. It was proof that white light is composite, a mixture. Each color corresponds to a specific wavelength of light. Red has the longest wavelength, violet the shortest. When all these wavelengths enter your eye at once, your brain interprets the mix as white. This principle is why rainbows form. Raindrops act like tiny prisms, bending sunlight and separating it into its component colors. It is also why the world around you is full of color. Objects absorb some wavelengths and reflect others. What you see is what bounces back. A rainbow is caused by light bending inside raindrops. Rainbows appear when sunlight and rain share the sky. Each raindrop acts as a miniature prism. When sunlight enters a droplet, it slows down and bends. This bending is called refraction. Inside the droplet, the light bounces off the back surface in a process called reflection. Then, as it exits, it bends again. Each color bends by a slightly different amount because each has a different wavelength. Red bends the least, violet bends the most. The result is that white sunlight spreads into a spectrum of colors. Millions of raindrops do this simultaneously, each one sending a specific color toward your eye, depending on its position in the sky. The arc of a rainbow is always centered opposite the sun. To see one, the sun must be behind you, and rain must be in front of you. The precise angle is 42 degrees from the line connecting the sun, your eye, and the droplet. This is why rainbows appear curved. You are seeing a cone of light, and your perspective reveals it as an arc. Double rainbows occur when light bounces twice inside the droplets. The colors appear reversed in the second arc because of the extra reflection. Rainbows are not objects you can approach or touch. They are patterns of light unique to your position. Two people standing side by side see slightly different rainbows because the droplets sending light to each of their eyes are not the same. Light slows down when it passes through materials like glass or water. In the emptiness of space, light moves at its maximum speed. But when it enters a material like water, glass, or even air, it slows down. This happens because light is an electromagnetic wave, and materials contain atoms with charged particles. As light passes through, it interacts with these particles, causing a delay. The denser the material, the more the light slows. In water, light travels at about 75% of its speed in a vacuum. In glass, it slows to around 67%. In diamond, one of the densest transparent materials, light moves at less than half its normal speed. This slowing is what causes refraction, the bending of light as it moves from one material to another. When light enters glass at an angle, one side slows down before the other, causing the beam to change direction. This is why a straw in a glass of water looks bent. The light reflecting off the submerged part bends as it exits the water, creating an illusion. Refraction is also what allows lenses to focus light. Eyeglasses, microscopes, telescopes, and cameras all rely on carefully shaped glass to bend light in useful ways. Without refraction, we would not have most of the optical tools that define modern life. The color of an object depends on which wavelengths it reflects. Nothing has color on its own. Color is a creation of light and perception. When white light shines on an object, the object absorbs some wavelengths and reflects others. The wavelengths that bounce back enter your eye and are interpreted as color. A red apple looks red because its surface absorbs most wavelengths, except red, which it reflects. A blue shirt absorbs red and yellow, but reflects blue. A white surface reflects all wavelengths equally. A black surface absorbs nearly everything. This is why black objects heat up faster in sunlight. They are absorbing the energy instead of reflecting it. The molecular structure of a material determines which wavelengths it absorbs. Different pigments, dyes, and compounds interact with light in different ways, creating the rich palette of the visible world. Interestingly, color is also contextual. The way your brain perceives color depends on surrounding light and nearby colors. This is why the same object can look different under fluorescent light versus sunlight. It is also why optical illusions involving color can be so startling. Your brain does not simply receive color, it interprets and constructs it. The sky is blue because of the way light scatters in the atmosphere. On a clear day, the sky glows blue. Not because it is reflecting the ocean or because space is blue, but because of a process called Rayleigh scattering. Sunlight entering Earth's atmosphere is made of all colors. As it travels through the air, it collides with molecules of nitrogen and oxygen. These molecules are much smaller than the wavelength of light. When light hits something that small, shorter wavelengths scatter more than longer ones. Blue and violet light have short wavelengths, so they scatter in every direction. Red and orange have longer wavelengths, so they pass through more directly. Your eye sees blue, scattered light coming from all parts of the sky, which is why the whole sky appears blue instead of showing the sun's white light. Violet scatters even more than blue, but our eyes are less sensitive to violet, and much of it is absorbed by the upper atmosphere, so we see blue. During sunrise and sunset, the story changes. Sunlight must pass through much more atmosphere to reach you, traveling a longer path. By the time it arrives, most of the blue has scattered away. What remains are the reds, oranges, and yellows, painting the sky in warm tones. This same principle explains why distant mountains look blue. Light from those mountains has scattered through more air, shifting the color you perceive. Sunsets are red because blue light scatters away first. As the sun sinks toward the horizon, its light must travel through a thicker slice of atmosphere to reach your eyes. The longer the path, the more opportunities for scattering. Blue and green wavelengths scatter away early, leaving the longer wavelengths, red, orange, and yellow, to dominate. This is why the sun itself appears redder at sunset, and why the sky near the horizon glows in warm colors. The effect is even more pronounced when the air contains dust, smoke, or water droplets. These particles scatter light differently than gas molecules, often enhancing reds and oranges. After a volcanic eruption, sunsets can become especially vivid for months as fine ash lingers in the atmosphere. Pollution can have a similar, though less dramatic effect. On worlds with different atmospheres, sunsets look different. Mars, for example, has a thin atmosphere, rich in fine dust. Sunsets there are blue, the opposite of Earth, because the dust scatters red light more effectively than blue. The color of a sunset is a signature of the air itself. Red light has the longest wavelength in the visible spectrum. The spectrum of visible light spans from red to violet. Red sits at one end with the longest wavelength, around 700 nanometers. A nanometer is 1/1000th of a meter. Violet sits at the other end with the shortest wavelength, around 400 nanometers. Between them lie orange, yellow, green, and blue. Wavelength determines not only color, but also energy. Longer wavelengths carry less energy. Shorter wavelengths carry more. This is why ultraviolet light, just beyond violet, can damage skin and cause sunburns. It carries more energy than visible light. Infrared, just beyond red, carries less and is felt as heat. Red light's long wavelength gives it certain advantages. It scatters less in the atmosphere, which is why red is used for warning lights and why astronomers use red light to preserve night vision. It also penetrates fog and smoke better than shorter wavelengths. This is why tail lights and brake lights are red. They remain visible even in poor conditions. In the deep ocean, red light is the first to be absorbed. Water filters it out within the first few meters. This is why everything looks blue-green at depth. The red wavelengths simply do not reach that far. Infrared light is invisible to us, but we can feel it as heat. Beyond the red edge of visible light lies infrared. We cannot see it, but we can feel it. Infrared radiation is what you sense as warmth from the sun, from a fire, or from any heated object. All objects with temperature emit infrared light. The warmer they are, the more they emit. Your own body radiates infrared constantly. This is how thermal cameras work. They detect infrared radiation and translate it into a visible image, revealing heat patterns invisible to the naked eye. Infrared has many uses. Astronomers use infrared telescopes to peer through cosmic dust and observe stars hidden from visible light. Night vision goggles detect infrared to see in complete darkness. Remote controls use infrared pulses to communicate with televisions and other devices. Even some animals can sense infrared. Pit vipers have specialized organs that detect the body heat of prey, allowing them to hunt in total darkness. Infrared is all around us, a hidden layer of the electromagnetic spectrum, carrying energy and information we cannot see but can often feel. Ultraviolet light exists just beyond violet and can damage living cells. On the other side of the spectrum, beyond violet, lies ultraviolet light. It carries more energy than visible light, enough to break chemical bonds and damage biological molecules. This is why too much exposure to ultraviolet radiation causes sunburns, skin aging, and increases the risk of skin cancer. DNA absorbs ultraviolet light, and when it does, the energy can cause mutations. Fortunately, Earth's atmosphere blocks most ultraviolet radiation from the sun. The ozone layer, a region of the upper atmosphere rich in ozone molecules, absorbs the most harmful ultraviolet wavelengths before they reach the surface. Without this shield, life on land would be far more difficult. Ultraviolet light is not entirely harmful. In moderate amounts, it helps our skin produce vitamin D, essential for bone health. It is also used to sterilize medical equipment and purify water because it kills bacteria and viruses. Some animals, including bees and certain birds, can see ultraviolet light. Flowers often have ultraviolet patterns, invisible to us, but visible to pollinators, guiding them to nectar. What looks plain to human eyes may be vividly patterned in ultraviolet. X-rays and gamma rays are even more energetic forms of light. Moving further along the electromagnetic spectrum, beyond ultraviolet, we encounter X-rays and gamma rays. These are forms of light with extremely short wavelengths and high energy. X-rays are produced when high-speed electrons collide with metal, releasing bursts of electromagnetic radiation. They can pass through soft tissue but are absorbed by denser materials like bone, which is why they are used in medical imaging. Gamma rays are even more energetic. They are produced by radioactive decay, nuclear reactions, and some of the most violent events in the universe, such as supernovae and black hole collisions. Gamma rays can penetrate most materials and are highly dangerous to living tissue. But they are also used in cancer treatment to destroy tumors. Both X-rays and gamma rays are invisible and intangible, yet they reveal hidden structures and carry the fingerprints of cosmic violence. They remind us that the spectrum of light extends far beyond what our eyes can detect, into realms of energy that shape everything from medicine to our understanding of the universe. Radio waves are the longest wavelengths of light. At the opposite end of the spectrum from gamma rays are radio waves. These have the longest wavelengths, ranging from millimeters to kilometers. Despite their size, they are still light, electromagnetic radiation traveling at the speed of light. Radio waves are used for communication. AM and FM radio, television broadcasts, cell phones, and Wi-Fi all rely on radio waves. to carry information through the air. Astronomers also use radio telescopes to study the universe. Many celestial objects emit radio waves, including pulsars, quasars, and the cold hydrogen gas that fills galaxies. Radio waves can pass through clouds, dust, and even some solid materials, making them incredibly useful for both communication and observation. Because their wavelengths are so long, radio waves carry less energy than visible light. They are safe, passing through our bodies constantly without harm. Right now, countless radio signals are moving through the space around you, invisible and unfelt, carrying voices, data, and information across vast distances. Microwaves sit between radio waves and infrared on the spectrum. Microwaves are a type of electromagnetic radiation with wavelengths shorter than radio waves but longer than infrared. They are commonly known for their use in microwave ovens, which heat food by causing water molecules to vibrate. The microwaves used in cooking have a specific frequency that resonates with water, transferring energy efficiently and warming the food from the inside. But microwaves have many other uses. Radar systems use microwaves to detect objects, measure distances, and track weather patterns. Satellites communicate with Earth using microwave signals because they can penetrate clouds and travel long distances without significant loss. Microwaves are also used in astronomy. The cosmic microwave background, the faint glow left over from the Big Bang, is a sea of microwave radiation that fills the entire universe. By studying it, scientists have learned about the age, composition, and structure of the cosmos. Microwaves, like all forms of light, are simply electromagnetic waves at a specific frequency, serving purposes both practical and profound. The electromagnetic spectrum is a continuous range of all possible wavelengths of light. Visible light, the part of the spectrum we can see, is just a tiny sliver of a much larger continuum. The electromagnetic spectrum includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. All of these are fundamentally the same thing: electromagnetic radiation, differing only in wavelength and energy. The spectrum is continuous. There are no gaps. Between red and infrared, there is a smooth transition. Between ultraviolet and X-rays, the same. Each type of radiation blends seamlessly into the next. What separates them is how they interact with matter and how much energy they carry. Our eyes evolved to detect a narrow band of wavelengths, the ones most abundant in sunlight and most useful for navigating the world. But the universe is filled with light we cannot see. Every object, every star, every galaxy emits radiation across the spectrum. To understand the cosmos fully, scientists build instruments to detect these invisible forms of light, expanding our vision far beyond the limits of human perception. Photons have no mass, but they carry momentum. Photons, the particles of light, are strange entities. They have no mass, no substance in the traditional sense. Yet they carry energy and momentum. When light strikes a surface, it exerts a tiny force. This is called radiation pressure. For everyday objects, the force is negligible. But in space, where there is no air resistance, radiation pressure can be significant. Solar sails, for example, are spacecraft propelled by the pressure of sunlight. Large reflective sails catch photons from the sun, and the accumulated momentum pushes the spacecraft forward. It is a slow process, but over time, a solar sail can reach impressive speeds without using any fuel. Radiation pressure also affects comets. As a comet approaches the sun, sunlight pushes on the gas and dust in its tail, causing the tail to always point away from the sun. Even though photons are massless, their momentum is real. It can move objects, transfer energy, and shape the behavior of matter across the universe. Light can be polarized, with waves vibrating in specific directions. Light is a transverse wave, meaning its oscillations are perpendicular to the direction it travels. Normally, light waves vibrate in all directions. But light can be polarized, filtered, so that waves vibrate in only one direction. Polarization occurs naturally when light reflects off surfaces like water or glass. The reflected light becomes partially polarized, with more waves vibrating horizontally than vertically. This is why polarized sunglasses reduce glare. They block horizontally polarized light, allowing only vertically polarized light to pass through. Polarization is also used in technology. Liquid crystal displays, or LCDs, in phones, computers, and televisions rely on polarized light to create images. The crystals twist the polarization of light passing through them, and by controlling this twisting, the display can control which pixels are bright and which are dark. Some animals can detect polarized light. Bees use it to navigate, even on cloudy days. Mantis shrimp have the most complex polarization vision known, able to see patterns invisible to almost all other creatures. Polarization is a hidden dimension of light, imperceptible to us, but fundamental to both nature and technology. Light can interfere with itself, creating patterns of brightness and darkness. When two light waves meet, they can interfere with each other. If the peaks of one wave align with the peaks of another, they add together, creating a brighter light. This is called constructive interference. If the peak of one wave aligns with the trough of another, they cancel each other out, creating darkness. This is called destructive interference. Interference creates beautiful patterns. In a classic experiment, light passing through two narrow slits creates alternating bands of light and dark on a screen. This happens because light from each slit travels slightly different distances to reach any given point on the screen. Where the distances differ by whole wavelengths, the waves reinforce. Where they differ by half wavelengths, they cancel. The result is an interference pattern, proof that light behaves as a wave. Interference is not just a laboratory curiosity. It is responsible for the colors in soap bubbles, oil slicks, and the iridescent wings of butterflies. Thin films of material cause light waves to reflect from both the top and bottom surfaces, and the interference between these reflections produces shifting colors depending on the thickness and the angle of view. The colors in soap bubbles come from thin film interference. A soap bubble shimmers with swirling colors that change as you move. These colors are not from pigments. They are created by interference. The bubble's wall is incredibly thin, just a few hundred nanometers. When light hits the bubble, some reflects off the outer surface, and some penetrates and reflects off the inner surface. These two reflected waves travel slightly different distances. If the difference is just right, certain colors interfere constructively and appear bright. Others interfere destructively and disappear. Because the bubble's thickness varies across its surface and changes as the bubble drains and thins, the colors shift and dance. The same principle creates colors in oil films on water. A thin layer of oil, just micrometers thick, reflects light from both its top and bottom surfaces. The interference between these reflections produces a rainbow of colors, even though the oil itself is clear. Thin film interference is also used in technology. Anti-reflective coatings on eyeglasses and camera lenses are thin films designed to cause destructive interference for reflected light, reducing glare and improving clarity. Diffraction causes light to bend around obstacles and spread through openings. Light does not always travel in straight lines. When it encounters an obstacle or passes through a narrow opening, it bends and spreads out. This is called diffraction. The effect is most noticeable when the size of the obstacle or opening is similar to the wavelength of light. When light passes through a small slit, it does not simply create a sharp shadow. Instead, it spreads into a pattern of bright and dark bands. This happens because different parts of the wavefront travel slightly different paths, and interference occurs. Diffraction is why you see a halo around a bright light when you squint. Your eyelashes create tiny slits, and the light diffracts as it passes through, spreading into patterns. Diffraction also limits the resolution of optical instruments. Telescopes and microscopes cannot resolve details smaller than about half the wavelength of light they use. This is why electron microscopes, which use electrons instead of light, can see much finer details. Electrons have much shorter wavelengths. Diffraction is a reminder that light is a wave, and waves do not respect sharp boundaries the way particles do. Holograms use interference and diffraction to create three-dimensional images. A hologram is a recording of an interference pattern created by light. When laser light is split into two beams, one beam reflects off an object and the other acts as a reference. The two beams meet on a photographic plate and their interference pattern is recorded. When the plate is illuminated with the same kind of light, the interference pattern diffracts the light in such a way that it recreates the original wavefront. The result is a three-dimensional image that appears to float in space. You can move around a hologram and see different perspectives, just as you would with a real object. Holograms are not just novelties. They are used in security features on credit cards and currency, in data storage, and in research. Some scientists envision holographic displays that could create interactive three-dimensional images without the need for special glasses. Holograms are a vivid demonstration of how interference and diffraction can be harnessed to manipulate light in extraordinary ways. Lasers produce light that is coherent and monochromatic. A laser is not just a bright light, it is a special kind of light. Laser light is coherent, meaning all the waves are synchronized, vibrating in step with each other. It is also monochromatic, meaning it consists of a single wavelength, a single pure color. Ordinary light, like that from a light bulb, is incoherent. The waves are jumbled, out of phase, and contain many wavelengths. This is why ordinary light spreads and diffuses quickly. Laser light, in contrast, can travel long distances with very little spreading. It can be focused to an incredibly tiny spot, concentrating energy with precision. Lasers are created using a process called stimulated emission. Atoms are excited to a higher energy state, and when they release that energy, they emit photons that stimulate other atoms to emit photons in exactly the same way. The result is a cascade of synchronized photons, all with the same wavelength and phase. Lasers are used in countless applications: cutting and welding materials, reading barcodes, performing delicate surgeries, measuring distances with extreme precision, and transmitting data through fiber optic cables. The coherent nature of laser light makes all of this possible. Fiber optic cables use total internal reflection to transmit light over long distances. Fiber optic cables are thin strands of glass or plastic that carry light signals over vast distances with minimal loss. They work using a principle called total internal reflection. When light traveling through a dense material like glass hits the boundary with a less dense material like air at a shallow angle, it does not pass through. Instead, it reflects back into the glass. Inside a fiber optic cable, light bounces back and forth along the walls, traveling down the length of the cable without escaping. This allows light to carry information, phone calls, internet data, television signals, across continents and under oceans. Fiber optics are faster and more efficient than electrical cables because light travels faster than electricity through copper and does not suffer from electromagnetic interference. A single fiber can carry thousands of separate signals at once by using different wavelengths of light, a technique called wavelength division multiplexing. The development of fiber optic technology has transformed global communication, enabling the high-speed internet and interconnected world we know today. Auroras are caused by solar particles exciting atoms in Earth's atmosphere. The aurora borealis in the north and aurora australis in the south are among the most beautiful light shows on Earth. These shimmering curtains of green, red, and purple light are caused by charged particles from the sun colliding with atoms in our atmosphere. The sun constantly emits a stream of particles called the solar wind. When a solar storm occurs, this wind intensifies, sending bursts of electrons and protons toward Earth. Our planet's magnetic field funnels these particles toward the poles, where they collide with oxygen and nitrogen atoms high in the atmosphere. The collisions transfer energy to the atoms, exciting their electrons to higher energy levels. When the electrons fall back down, they release the energy as light. Oxygen emits green and red light. Nitrogen emits blue and purple. The colors and patterns of an aurora depend on which atoms are being excited and at what altitude. Auroras occur high above the surface, typically between 100 and 300 kilometers up. They are visible from the ground as dancing lights, but astronauts in orbit see them from above, glowing rings encircling the poles. Auroras are a visible connection between the sun and Earth, a reminder that space is not empty but filled with flows of energy. Bioluminescence is light produced by living organisms through chemical reactions. In the deep ocean, in tropical forests, and even in your backyard, some creatures make their own light. This is called bioluminescence. It occurs when a chemical reaction inside an organism produces light without heat. The most common system involves a molecule called luciferin and an enzyme called luciferase. When luciferin reacts with oxygen in the presence of luciferase, it releases energy in the form of light. Fireflies use bioluminescence to attract mates. Each species has its own flashing pattern, a code that helps them find each other in the dark. Deep-sea creatures use it for many purposes. Some use it to lure prey, others to confuse predators, and some to communicate. Certain squid can produce light in patterns across their bodies, creating displays that ripple and pulse. Bioluminescence is almost always blue or green because these colors travel farthest in water. Some fungi glow in the dark, their mycelium emitting a faint green light. Scientists still do not fully understand why they do this, though it may attract insects that help disperse their spores. Bioluminescence is cold light, nearly 100% efficient, unlike incandescent bulbs that waste most of their energy as heat. Phosphorescence allows materials to glow in the dark after being exposed to light. Some materials absorb light and then release it slowly over time, glowing softly in the dark. This is called phosphorescence. It happens when light excites electrons in the material to a higher energy state, but instead of dropping back down immediately, they get trapped. Over minutes or hours, they gradually fall back, releasing light as they do. Glow-in-the-dark stars on a bedroom ceiling work this way. You expose them to light, and they absorb energy. When you turn off the lights, they glow as the stored energy is slowly released. Phosphorescent materials are used in emergency exit signs, watch dials, and safety markers. They need no batteries or electricity. Once charged with light, they glow on their own. The glow fades over time as the stored energy is used up. A related phenomenon is fluorescence, where materials absorb light and re-emit it immediately. Highlighter ink is fluorescent. It absorbs ultraviolet light and emits visible light, making it appear unnaturally bright. Phosphorescence and fluorescence are both forms of luminescence, light emitted by a substance without being heated. Our eyes contain 3 types of color receptors called cones. Human color vision is made possible by specialized cells in the retina called cones. There are 3 types of cones, each sensitive to different wavelengths of light. One type responds most strongly to short wavelengths, which we perceive as blue. Another responds to medium wavelengths, perceived as green. The third responds to long wavelengths, perceived as red. Every color you see is a combination of signals from these 3 types of cones. When red and green cones are stimulated equally, you perceive yellow. When all 3 are stimulated, you see white. When none are stimulated, you see black. This is called trichromatic vision. It is why screens and printers can recreate almost any color using just 3 primary colors. Your brain does the rest, blending the signals into the rich spectrum of hues you experience. Not everyone has the same color vision. Color blindness occurs when 1 or more types of cones are missing or do not function properly. The most common form, red-green color blindness, makes it difficult to distinguish between reds and greens. Some people are born with 4 types of cones, a condition called tetrachromacy. They may be able to see subtle differences in color that most people cannot. Some animals see colors that humans cannot perceive. While humans have 3 types of color receptors, many animals have more, or different types. Birds, for example, often have 4 types of cones, including one that detects ultraviolet light. To a bird, the world is filled with colors we cannot imagine. Flowers that look plain to us may have vivid ultraviolet patterns, visible to bees and birds, guiding them to nectar. Mantis shrimp have 16 types of color receptors, far more than any other known animal. Scientists are still trying to understand how their brains process this information. They may perceive color in a fundamentally different way than we do. Some snakes can see infrared light using specialized pit organs, allowing them to detect the body heat of prey in total darkness. Dogs and cats, on the other hand, have only 2 types of cones. They see fewer colors than we do, roughly similar to a human with red-green color blindness. Their world is not black and white, but it is less colorful than ours. These differences remind us that color is not an inherent property of the world. It is a construct of perception, shaped by the biology of the observer. Color is a construct of the brain, not an inherent property of objects. Color does not exist in the external world. It is created by your brain. Objects emit or reflect light of certain wavelengths, but those wavelengths are not colored. They are simply electromagnetic waves. Color is the brain's way of interpreting those wavelengths. When light enters your eye, it stimulates cones in the retina. The cones send signals to the brain, which processes them and assigns a color. This means color is subjective. What you call red is an experience that happens inside your mind. There is no way to know if the red you see is the same as the red someone else sees. You both learn to call it red, but the internal experience might differ. This subjectivity is most obvious in cases of color perception illusions. The famous dress photo, where some people see blue and black while others see white and gold, reveals how much the brain relies on context to determine color. Your brain makes assumptions about lighting and shadows, and those assumptions can lead to different interpretations. Color is a tool your brain uses to make sense of the world, a layer of meaning imposed on the raw data of light. Prisms split white light into a spectrum because different colors refract by different amounts. When white light enters a prism, it slows down and bends, but not all colors bend by the same amount. Blue light, with its shorter wavelength, bends more than red light. This causes the colors to spread out into a spectrum as they pass through the prism. When the light exits the prism, it bends again, spreading the colors even further. The result is the familiar rainbow of red, orange, yellow, green, blue, and violet. This process is called dispersion. It occurs because the refractive index of glass depends on wavelength. Dispersion is also responsible for chromatic aberration in lenses, where different colors focus at slightly different points, creating a blurred or fringed image. Modern lenses are designed with multiple elements to correct for this. Dispersion reveals a fundamental truth. White light is not simple. It is a mixture, and a prism teases apart its components, revealing the hidden spectrum within. Diamonds sparkle because of their high refractive index and dispersion. Diamonds are prized for their brilliance and fire. Brilliance is the white light reflected from a diamond's surface and interior. Fire is the flashes of color that appear as the diamond moves. Both are caused by the diamond's optical properties. Diamond has an extremely high refractive index, much higher than glass. This means light slows down significantly when it enters a diamond and bends sharply. A well-cut diamond is shaped so that light entering from the top reflects multiple times inside before exiting, maximizing the amount of light returned to the viewer. This creates brilliance. Diamond also has high dispersion, meaning it separates white light into colors more effectively than most materials. As light bounces inside the diamond, it splits into a spectrum, and different colors exit at different angles. This creates the flashes of rainbow color known as fire. Cut is crucial. A poorly cut diamond will allow light to leak out the bottom or sides, reducing brilliance. A master cutter shapes the facets to precise angles, turning the stone into a dazzling display of light and color. Mirages are caused by light bending through layers of air at different temperatures. On a hot day, you might see what looks like water shimmering on the road ahead, only to have it disappear as you approach. This is a mirage. It is caused by refraction in the atmosphere. When the ground is very hot, the air just above it heats up and becomes less dense than the cooler air above. Light traveling from the sky toward the ground bends as it passes through these layers of different density. At a shallow angle, the light bends upward before reaching the ground. Your brain interprets this light as if it traveled in a straight line, so it appears to be coming from below the horizon, creating the illusion of a reflective surface like water. Mirages are most common in deserts and on paved roads in summer. There are also superior mirages, where cold air near the surface bends light downward, causing distant objects to appear elevated or even inverted. These are common in polar regions and over cold bodies of water. Mirages are not hallucinations. They are real optical phenomena, light behaving in predictable ways as it moves through the atmosphere. Moonlight is just reflected sunlight. The moon does not produce its own light. It shines because it reflects sunlight. When you look at the moon, you are seeing light that traveled from the sun, struck the moon's surface, and bounced back toward Earth. The moon reflects only about 12% of the sunlight that hits it. The rest is absorbed. This is why the moon is not blindingly bright like the sun. Moonlight is the same spectrum as sunlight, but much dimmer. Interestingly, moonlight can appear bluer than sunlight. This is partly an illusion caused by the way our eyes work. In low light, our color vision diminishes and our sensitivity to blue increases. This shift, called the Purkinje effect, makes blue tones more noticeable in moonlight. Moonlight has inspired countless myths, poems, and songs. It has a calming, mysterious quality. But physically, it is simply sunlight at second hand, a gentle reminder of the sun even in the darkest night. The moon's phases are caused by the changing angle of sunlight hitting its surface. The moon orbits Earth, and as it does, the angle between the sun, the moon, and Earth changes. This changes how much of the moon's sunlit side we can see. When the moon is between Earth and the sun, the side facing us is dark. This is a new moon. As the moon moves in its orbit, more of the sunlit side becomes visible. A crescent appears, then a half moon, then a gibbous moon, and finally a full moon, when the entire sunlit side faces Earth. Then, the cycle reverses, as the moon continues its orbit. The phases are not caused by Earth's shadow. That would be an eclipse. The phases are simply the result of perspective. The moon is always half lit by the sun, but we see different portions of that lit half depending on where the moon is in its orbit. This cycle takes about 29.5 days, the origin of the month in many calendars. Eclipses occur when the sun, Earth, and moon align. A solar eclipse happens when the moon passes directly between Earth and the sun, casting a shadow on Earth's surface. If you are in that shadow, the sun appears partially or completely blocked. A total solar eclipse, where the sun is entirely covered, is one of the most dramatic natural events. The sky darkens, stars appear, and the sun's outer atmosphere, the corona, becomes visible as a glowing halo. Solar eclipses are rare at any given location because the moon's shadow is small and sweeps across only a narrow path. A lunar eclipse occurs when Earth passes between the sun and the moon, casting its shadow on the moon. Unlike a solar eclipse, a lunar eclipse is visible from anywhere on the night side of Earth. The moon does not disappear. Instead, it often turns a deep red. This is because Earth's atmosphere bends and scatters sunlight, and the red wavelengths, which scatter least, are refracted into the shadow, bathing the moon in a dim red glow. This is sometimes called a blood moon. Eclipses have fascinated humans for millennia, and ancient astronomers learned to predict them with remarkable accuracy. Total internal reflection can create optical illusions underwater. When you are underwater and look up at the surface, you see a bright circle surrounded by darkness. This is caused by total internal reflection. Light entering the water from above refracts toward the normal, bending as it slows down. When you look up from below, light leaving the water does the opposite. It bends away from the normal. At a certain angle, called the critical angle, the light bends so much that it travels along the surface instead of leaving the water. Beyond this angle, light cannot escape. It reflects back down. From underwater, this means you can only see out of the water within a cone of about 97 degrees. Outside that cone, you see reflections of the underwater environment. The surface acts like a mirror. This creates a surreal view, a window to the sky surrounded by a mirror of the depths. Fish and divers experience this every day, a reminder that the behavior of light changes dramatically at the boundary between two materials. Fiber optics revolutionized communication by transmitting light through glass. Before fiber optics, long-distance communication relied on electrical signals traveling through copper wires. These signals degraded over distance and were vulnerable to interference. Fiber optic cables changed everything. By encoding information in pulses of light and sending them through strands of glass, engineers achieved faster, clearer, and more efficient communication. A single optical fiber, thinner than a human hair, can carry thousands of phone calls or stream high-definition video without degradation. Light does not suffer from electromagnetic interference the way electricity does, and it can travel much farther before needing amplification. Undersea fiber optic cables now connect continents, carrying the vast majority of international internet traffic. The development of low-loss optical fiber in the 1970s was a breakthrough. Early fibers lost so much light that they were impractical. Modern fibers are so pure that light can travel hundreds of kilometers with minimal loss. This purity, combined with the principle of total internal reflection, made the global fiber optic network possible. Lenses focus light by refracting it through a curved surface. A lens is a piece of transparent material, usually glass, with at least one curved surface. When light passes through a lens, it refracts, bending according to the shape of the lens. A convex lens, thicker in the middle than at the edges, bends light inward, causing parallel rays to converge at a point called the focus. This is how magnifying glasses, cameras, and eyeglasses for farsightedness work. A concave lens, thinner in the middle, bends light outward, causing rays to diverge. This is used in eyeglasses for nearsightedness. By carefully shaping the curvature of a lens, opticians can control exactly how light bends, correcting vision, magnifying tiny details, or focusing starlight in a telescope. Compound lenses, made of multiple elements, can correct for aberrations and distortions that single lenses produce. The human eye itself is a sophisticated optical system with a lens that changes shape to focus on objects at different distances. Understanding lenses is understanding how we see. Telescopes gather and focus light to see distant objects. Telescopes are devices that collect light from distant objects and bring it to a focus, making faint things visible. There are two main types. Refracting telescopes use lenses to bend light. Reflecting telescopes use curved mirrors. Reflecting telescopes are more common in modern astronomy because mirrors can be made larger and do not suffer from chromatic aberration. The larger the mirror or lens, the more light the telescope can gather and the fainter the objects it can see. Telescopes also magnify, making distant objects appear closer. The Hubble Space Telescope, orbiting above Earth's atmosphere, has revealed galaxies billions of light-years away, nebulae where stars are born, and planets around other suns. Ground-based telescopes, some with mirrors 10 meters across, peer into the universe with incredible clarity. Adaptive optics correct for the blurring caused by Earth's atmosphere, allowing these telescopes to rival space-based instruments. Every photon that reaches a telescope carries information, a message, from across space and time, and telescopes are the tools we use to decode those messages. Microscopes use lenses to magnify tiny objects and reveal hidden worlds. Just as telescopes extend our vision outward, microscopes extend it inward. A simple microscope is just a magnifying glass, a single convex lens that makes small things appear larger. A compound microscope uses two lenses, an objective lens near the object and an eyepiece lens near your eye. Together, they can magnify an object hundreds or even thousands of times. This reveals structures invisible to the naked eye. Cells, bacteria, the intricate patterns of insect wings, the fibers of fabric. Microscopes opened up entire realms of biology and medicine. The discovery of cells, bacteria, and other microorganisms transformed our understanding of life and disease. Light microscopes have limits. They cannot resolve details smaller than about half the wavelength of light, roughly 200 nanometers. To see smaller structures, scientists use electron microscopes, which use beams of electrons instead of light. Electrons have much shorter wavelengths, allowing electron microscopes to reveal viruses, molecules, and even individual atoms. Cameras capture light and record images using sensors or film. A camera is a device that captures light and preserves it as an image. Traditional cameras used film, a material coated with light-sensitive chemicals. When light struck the film, it caused a chemical reaction, recording the pattern of light and shadow. Developing the film made the image visible and permanent. Modern cameras use digital sensors instead of film. These sensors contain millions of tiny light-sensitive elements called pixels. Each pixel measures the amount of light hitting it, and together they create a digital image. Color cameras use filters so that each pixel captures red, green, or blue light. The camera's processor combines this information to produce a full-color image. Cameras use lenses to focus light onto the film or sensor, and a shutter controls how long the light is allowed in. Adjusting the shutter speed, aperture, and sensitivity allows photographers to capture everything from a frozen moment in bright sunlight to a long exposure of stars wheeling across the night sky. Cameras are tools for preserving light, for holding on to a moment and making it permanent. Polarized sunglasses reduce glare by blocking horizontally polarized light. Glare occurs when light reflects off surfaces like water, roads, or snow. Reflected light becomes partially polarized, with more light waves vibrating horizontally than vertically. This horizontal polarization is what causes the bright, harsh glare that makes it hard to see. Polarized sunglasses have a special filter that blocks horizontally polarized light while allowing vertically polarized light to pass through. This dramatically reduces glare without significantly darkening your overall view. Fishermen use polarized sunglasses to see beneath the surface of the water. Drivers use them to reduce glare from the road. Photographers use polarizing filters to reduce reflections and enhance colors, especially in skies and bodies of water. Polarization is an invisible property of light, but it has very visible effects, and learning to control it opens up new ways of seeing the world. Light pollution washes out the night sky and affects wildlife. In cities and towns, artificial lights brighten the night sky, making it difficult or impossible to see stars. This is called light pollution. Streetlights, buildings, advertising signs, and outdoor lighting scatter off particles in the atmosphere, creating a glow that overwhelms the faint light from stars and galaxies. In the darkest places on Earth, thousands of stars are visible. In a typical city, you might see only a few dozen. Light pollution is not just an inconvenience for stargazers. It affects wildlife. Many animals rely on natural cycles of light and dark to regulate their behavior. Migrating birds can become disoriented by city lights. Sea turtle hatchlings, which instinctively move toward the brightest horizon, the ocean reflecting moonlight, are confused by lights from buildings and roads. Nocturnal animals have their hunting and mating disrupted. Even humans are affected. Exposure to bright light at night can interfere with sleep and disrupt circadian rhythms. Efforts to reduce light pollution include using shielded fixtures that direct light downward, dimming lights when not needed, and choosing warmer colored lights that scatter less. The night sky is a shared heritage, and preserving it requires conscious choices about how we light our world. Sunlight provides energy that drives almost all life on Earth. The sun is the ultimate source of energy for nearly every living thing on this planet. Plants use sunlight to power photosynthesis, converting carbon dioxide and water into sugars and oxygen. This process captures energy from light and stores it in chemical bonds. Herbivores eat plants and gain that energy. Carnivores eat herbivores. Energy flows through the food chain, but it all traces back to sunlight. Even fossil fuels, coal, oil, and natural gas are stored sunlight. They formed from ancient plants and microorganisms that captured solar energy millions of years ago. When we burn them, we release that ancient light as heat and motion. Only a few ecosystems do not rely on sunlight. Deep-sea hydrothermal vents, for example, support life using energy from Earth's interior. But these are exceptions. For the vast majority of life, the sun is everything. It warms the planet, drives the water cycle, creates weather, and provides the energy that makes growth and movement possible. Without the sun, Earth would be a frozen, lifeless rock. Photosynthesis converts light energy into chemical energy. Photosynthesis is one of the most important processes on Earth. It occurs in plants, algae, and some bacteria. These organisms contain a molecule called chlorophyll, which absorbs light, primarily in the blue and red wavelengths. This is why plants appear green. They reflect the green light, they do not absorb. The absorbed light energy is used to split water molecules into hydrogen and oxygen. The oxygen is released into the air, and the hydrogen is used to convert carbon dioxide into glucose, a sugar that stores energy. This process takes place in structures called chloroplasts, which contain layers of membranes where light is captured and energy is transferred. Photosynthesis is why we have oxygen to breathe. Billions of years ago, early photosynthetic organisms filled the atmosphere with oxygen, transforming the planet and making complex life possible. Today, photosynthesis continues to produce the oxygen we need and remove carbon dioxide from the atmosphere. It is a bridge between light and life, turning the energy of the sun into the fuel that powers the living world. Chlorophyll absorbs red and blue light, but reflects green. Chlorophyll is the molecule that makes photosynthesis possible. It has a complex structure that allows it to capture light energy. Chlorophyll absorbs light most efficiently in the red and blue parts of the spectrum. It does not absorb green light well. Instead, it reflects it. This is why leaves appear green. The color you see is the color the chlorophyll does not use. In autumn, when chlorophyll breaks down, other pigments in the leaves become visible. Carotenoids, which are yellow and orange, and anthocyanins, which are red and purple, create the vibrant colors of fall foliage. These pigments were always there, but the green chlorophyll masked them. When the chlorophyll disappears, the hidden colors emerge. Different types of chlorophyll exist, each absorbing slightly different wavelengths. This allows plants to capture a broader range of light. Some photosynthetic bacteria even use pigments that absorb infrared light, extending the range of usable sunlight beyond what is visible to us. Different wavelengths of light penetrate water to different depths. Water absorbs light, but not evenly across the spectrum. Red light is absorbed quickly, within the first few meters. Orange follows. Yellow penetrates a bit deeper. Green and blue light reach the farthest, which is why the ocean appears blue. In the deep sea, only blue light remains, and below a certain depth, no sunlight penetrates at all. This affects marine life. Red creatures appear black at depth because there is no red light to reflect. Some deep-sea fish are bioluminescent, producing their own blue or green light to see and communicate. Aquatic plants near the surface have chlorophyll adapted to the full spectrum. Deeper aquatic plants often have additional pigments to capture the blue and green light that reaches them. The absorption of light by water also affects temperature. The surface warms quickly because it absorbs sunlight. Deeper water stays cold because little light reaches it. This layering, combined with currents and mixing, shapes ocean ecosystems and climate. Seasons are caused by the tilt of Earth's axis, which changes the angle of sunlight. Earth's axis is tilted at an angle of about 23.5 degrees relative to its orbit around the Sun. This tilt means that different parts of Earth receive different amounts of sunlight at different times of the year. When the North Pole is tilted toward the Sun, the Northern Hemisphere receives more direct sunlight and experiences summer. The Southern Hemisphere, tilted away, receives less direct light and experiences winter. 6 months later, the situation reverses. The tilt does not change. What changes is Earth's position in its orbit, which alters which hemisphere is tilted toward the Sun. The angle of sunlight matters because light hitting at a steep angle spreads over a larger area and is less intense. Light hitting directly is concentrated and more intense. This is why the sun feels stronger in summer and weaker in winter. It is also why polar regions are cold. Even in summer, sunlight arrives at a shallow angle. Seasons are a dance between Earth and the Sun, driven by geometry and light. The greenhouse effect traps infrared light and warms the planet. Sunlight passes through Earth's atmosphere and warms the surface. The warm surface then radiates energy back towards space, but not as visible light. It radiates as infrared, which has longer wavelengths and lower energy. Certain gases in the atmosphere, carbon dioxide, methane, water vapor, and others, absorb infrared light. They trap it, preventing it from escaping to space. The trapped energy warms the atmosphere, which in turn warms the surface. This is the greenhouse effect. It is named after greenhouses, which trap heat using glass, though the mechanisms are different. The greenhouse effect is natural and necessary. Without it, Earth would be much colder, too cold for most life. But human activities have increased the concentration of greenhouse gases, intensifying the effect and warming the planet beyond natural levels. This is the core of climate change. Understanding the greenhouse effect requires understanding how different wavelengths of light interact with matter. Visible light passes through the atmosphere easily. Infrared does not. This difference, driven by the properties of light, shapes the temperature of our world. Ozone in the upper atmosphere absorbs harmful ultraviolet light. Earth's atmosphere contains a layer of ozone, a molecule made of 3 oxygen atoms concentrated in the stratosphere. Ozone has a unique property. It absorbs ultraviolet light, particularly the most harmful wavelengths. When ultraviolet light strikes an ozone molecule, the energy breaks it apart. But in the process, the ultraviolet light is absorbed and does not reach the surface. This protects life on Earth. Ultraviolet radiation can damage DNA, cause skin cancer, harm eyes, and disrupt ecosystems. Before the ozone layer formed, life on land was not possible. Early photosynthetic organisms in the ocean produced oxygen, and some of that oxygen was converted into ozone by sunlight. Over millions of years, the ozone layer built up, creating a shield that allowed life to colonize the land. In the late 20th century, scientists discovered that human-made chemicals called chlorofluorocarbons, or CFCs, were destroying the ozone layer. CFCs release chlorine atoms when broken down by sunlight, and those chlorine atoms catalyze the destruction of ozone. International agreements banned CFCs, and the ozone layer is slowly recovering. It is a story of light, chemistry, and the delicate balance that makes life possible. Lightning produces light through the rapid heating of air. Lightning is a massive electrical discharge between clouds or between a cloud and the ground. The current can reach tens of thousands of amperes, and the temperature of the lightning channel can exceed 30,000 degrees Celsius, hotter than the surface of the sun. This extreme heat causes the surrounding air to expand explosively, creating the sound we hear as thunder. It also causes the air to glow. The intense energy excites nitrogen and oxygen molecules, raising their electrons to higher energy levels. When the electrons fall back, they release light. The color depends on which gases are excited and how much energy they have. Most lightning appears white or blue-white because multiple wavelengths are emitted. Occasionally, lightning can appear orange, red, or even purple, depending on the presence of dust, moisture, or other atmospheric conditions. The light from lightning is brief but brilliant, a visible reminder of the immense power of electrical storms. Thunder and lightning are inseparable. Light travels much faster than sound, so you see the flash before you hear the rumble. By counting the seconds between them, you can estimate how far away the lightning struck. Neon signs glow because electricity excites gas atoms. Neon signs produce their distinctive glow using a simple principle. A glass tube is filled with a low-pressure gas, often neon but sometimes other gases like argon or xenon. Electrodes at each end of the tube create an electric field. When electricity flows, it strips electrons from gas atoms, creating a plasma. The free electrons collide with other atoms, transferring energy. This energy excites the atoms, raising their electrons to higher energy levels. When the electrons fall back down, they release the energy as light. The color of the light depends on the gas. Neon emits a bright orange-red. Argon produces a pale blue. By mixing gases or coating the inside of the tube with phosphors, different colors can be achieved. Neon signs are not just advertising. They are physics made visible, a demonstration of how light and energy interact at the atomic level. The glow is distinctive and warm, a signature of excited atoms returning to rest. Incandescent bulbs produce light by heating a filament until it glows. An incandescent light bulb works by passing electricity through a thin wire called a filament, usually made of tungsten. The resistance of the wire causes it to heat up. As the temperature rises, the filament begins to glow. First red, then orange, then yellow, and finally white. This is called incandescence. The light produced depends on temperature. Hotter objects emit more light and shift toward shorter wavelengths. A very hot filament emits white light, a mix of all visible colors. Incandescent bulbs are simple and produce a warm, pleasant light, but they are inefficient. Most of the energy goes into heat, not light. Only about 5% of the energy is converted into visible light. The rest is wasted as infrared. This is why incandescent bulbs get very hot and why they have largely been replaced by more efficient technologies like LEDs and fluorescent lights. But for over a century, the incandescent bulb was the standard, a symbol of electric light and progress, all thanks to the principle that hot things glow. Fluorescent lights use electricity to excite mercury vapor, which emits ultraviolet light. Fluorescent lights are more efficient than incandescent bulbs. They work by passing electricity through a gas, usually mercury vapor, inside a tube. The electricity excites the mercury atoms, which emit ultraviolet light. Ultraviolet is invisible to us, so the inside of the tube is coated with a phosphor, a material that absorbs ultraviolet and re-emits it as visible light. The color of the light depends on the phosphor coating. By choosing different phosphors, manufacturers can create warm white, cool white, or even colored light. Fluorescent lights produce much less heat than incandescent bulbs and last longer, but they contain small amounts of mercury, which is toxic, so they must be disposed of carefully. Compact fluorescent lights, or CFLs, brought fluorescent technology into standard light bulb sockets, offering energy savings. They were a step toward more efficient lighting, though they have now largely been surpassed by LEDs. LEDs produce light through electroluminescence. Light-emitting diodes, or LEDs, represent a revolution in lighting. They are small, efficient, and long-lasting. LEDs produce light through a process called electroluminescence. They are made of semiconductor materials, substances that conduct electricity under certain conditions. When electricity flows through the semiconductor, electrons move from one layer to another. As they do, they release energy in the form of photons. The color of the light depends on the materials used. Different semiconductors emit different wavelengths. Red LEDs use aluminium gallium arsenide. Blue LEDs, a breakthrough that earned a Nobel Prize, use gallium nitride. White LEDs combine a blue LED with a phosphor coating that converts some of the blue light to yellow. Together, blue and yellow create white light. LEDs are incredibly efficient, converting most of their energy into light rather than heat. They last for tens of thousands of hours, far longer than incandescent or fluorescent lights. They are used everywhere, from screens to indicators to home lighting. The development of LEDs has transformed how we light the world, reducing energy consumption and environmental impact. Screens create images using tiny red, green, and blue lights called pixels. The screen you are looking at, whether it is a phone, computer, or television, creates images using countless tiny dots of light called pixels. Each pixel is made of 3 subpixels, one red, one green, and one blue. By varying the brightness of each subpixel, the screen can create any color. If all 3 are bright, the pixel appears white. If all are dark, it appears black. If only red and green are bright, the pixel appears yellow. This is called additive color mixing. It works because of how our eyes perceive color. Our 3 types of cones respond to red, green, and blue light, and the brain blends these signals. Screens exploit this by directly stimulating the cones with precise combinations of light. The resolution of a screen is determined by how many pixels it has. More pixels mean finer detail. Modern screens pack millions of pixels into small areas, creating images so sharp that individual pixels are invisible at normal viewing distances. The technology varies. LCD screens use liquid crystals and backlights. OLED screens have pixels that emit their own light, but the principle is the same. Combine red, green, and blue light in precise amounts, and you can create any image. The electromagnetic spectrum includes many types of radiation beyond visible light. Visible light is a tiny part of a vast continuum called the electromagnetic spectrum. This spectrum includes, in order of increasing wavelength, gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. All of these are the same fundamental phenomenon, electromagnetic radiation, differing only in wavelength and energy. Each type has unique properties and uses. Gamma rays have the shortest wavelengths and highest energy, capable of penetrating most materials and used in cancer treatment and sterilization. X-rays are slightly less energetic but still able to pass through soft tissue, making them invaluable in medical imaging. Ultraviolet, just beyond violet, causes sunburns but also helps produce vitamin D and is used for disinfection. Visible light is the narrow band our eyes detect. Infrared is felt as heat and used in thermal imaging. Microwaves cook food and transmit data. Radio waves have the longest wavelengths and are used for broadcasting and communication. Together, these form the full spectrum of light, most of which is invisible to us but essential to modern life and our understanding of the universe. Black holes can emit light through processes near their event horizon. Black holes are regions of space where gravity is so strong that not even light can escape. Once something crosses the event horizon, the boundary of the black hole, it is lost forever. Yet, black holes can be associated with some of the brightest phenomena in the universe. As matter falls toward a black hole, it forms an accretion disk, a swirling disk of gas and dust. Friction and compression heat this material to millions of degrees, causing it to emit intense light, especially in X-rays. This light comes from outside the event horizon, so it can escape. Some black holes also produce jets, narrow beams of particles and radiation that shoot out perpendicular to the accretion disk at nearly the speed of light. These jets can extend for thousands of light years and shine brilliantly across the spectrum. There is also Hawking radiation, a theoretical form of radiation predicted by physicist Stephen Hawking. Near the event horizon, quantum effects can cause particle pairs to form, and one particle may escape while the other falls in. Over unimaginable timescales, this process could cause black holes to slowly evaporate. Black holes are not entirely black. They are surrounded by light, created by the very matter they consume. Stars produce light through nuclear fusion in their cores. Stars shine because of nuclear fusion. Deep in the core of a star, temperatures and pressures are so extreme that hydrogen nuclei collide and fuse together, forming helium. This process releases energy in the form of light and heat. The energy produced in the core radiates outward, taking thousands to millions of years to reach the surface. Once it reaches the surface, it escapes into space as starlight. The color of a star depends on its temperature. Cooler stars, around 3000 degrees Celsius, glow red. Hotter stars, like our Sun at about 5500 degrees, appear yellow-white. The hottest stars, exceeding 30,000 degrees, shine blue. This relationship between temperature and color is described by Wien's law, which states that the peak wavelength of light emitted by an object shifts to shorter wavelengths as temperature increases. Stars are not all the same. They vary in size, mass, temperature, and lifespan, but they all share the same basic process. They are fusion reactors, converting mass into energy, and that energy streams outward as light, illuminating the cosmos. The Sun emits a spectrum of light called the solar spectrum. The Sun produces light across a wide range of wavelengths, from ultraviolet through visible into infrared. When this light is split by a prism or diffraction grating, it creates the solar spectrum. The spectrum is not smooth. It contains dark lines, called absorption lines. These are wavelengths where light has been absorbed by elements in the Sun's outer layers. Each element absorbs light at specific wavelengths, creating a unique pattern of lines. By studying these lines, scientists can determine the composition of the Sun without ever visiting it. Hydrogen, helium, iron, calcium, and many other elements have been identified this way. The solar spectrum also reveals the Sun's temperature, motion, and magnetic activity. It is a fingerprint, a detailed record encoded in light. The same technique is used to study distant stars, planets, and galaxies. Spectroscopy, the study of spectra, has become one of the most powerful tools in astronomy, allowing us to decode the light from across the universe. Redshift occurs when light stretches as objects move away from us. When an object emitting light moves away from you, the light waves stretch, increasing their wavelength. This shifts the light toward the red end of the spectrum, a phenomenon called redshift. It is similar to the Doppler effect with sound, where a siren sounds lower as it moves away. Redshift is crucial in astronomy. By measuring the redshift of light from distant galaxies, astronomers can determine how fast those galaxies are moving away. In the 1920s, Edwin Hubble discovered that nearly all galaxies show redshift, and the farther away they are, the greater the redshift. This led to the realization that the universe is expanding. Space itself is stretching, carrying galaxies away from each other. The most distant galaxies have enormous redshifts, their light stretched so much that ultraviolet light becomes visible or even infrared. Redshift is a measure of both motion and cosmic expansion, a key piece of evidence for the Big Bang and the dynamic nature of the universe. Blueshift occurs when light compresses as objects move toward us. Just as redshift occurs when an object moves away, blueshift occurs when it moves toward you. The light waves compress, decreasing their wavelength and shifting toward the blue end of the spectrum. Blueshift is less common in astronomy because the universe is expanding and most galaxies are moving away. But some objects do show blueshift. The Andromeda Galaxy, our nearest large neighbor, is moving toward the Milky Way and shows a slight blueshift. In a few billion years, the two galaxies will collide and merge. Stars within our own galaxy can also show blueshift if they are moving toward us. Astronomers use both redshift and blueshift to map the motion of objects in space, revealing the dynamics of galaxies, clusters, and the universe as a whole. These shifts, encoded in light, are windows into motion and time. Gravitational lensing bends light around massive objects. General relativity predicts that massive objects warp the fabric of space and time. Light, traveling through this warped space, follows a curved path. This is called gravitational lensing. When light from a distant object passes near a massive foreground object, like a galaxy or a black hole, the light bends. From our perspective, the distant object can appear distorted, magnified, or even duplicated. Sometimes the distant object forms a ring around the massive object, called an Einstein ring. Gravitational lensing has been used to study dark matter, the invisible substance that makes up most of the mass in the universe. Dark matter does not emit light, but it does warp space, and astronomers can detect its presence by observing how it lenses light from more distant objects. Lensing also allows astronomers to see extremely distant galaxies that would otherwise be too faint to detect. The massive object acts like a natural telescope, magnifying the light from behind it. Gravitational lensing is a direct confirmation that space can be curved and that mass bends light. Cherenkov radiation is light emitted when particles travel faster than light in a medium. Nothing can travel faster than light in a vacuum, but light slows down in materials like water or glass. Particles can travel faster than this reduced speed, and when they do, they emit a strange blue glow called Cherenkov radiation. This happens in nuclear reactors. Charged particles moving through water faster than light can travel in water, create a shock wave of light, similar to a sonic boom. The glow is eerie and beautiful, a sign of particles moving at relativistic speeds. Cherenkov radiation is used to detect high-energy particles in experiments and to study cosmic rays. Detectors filled with water or ice can observe the faint blue glow when neutrinos, nearly massless particles from space, interact with the medium. It is a visible sign of the invisible, light-revealing particles that would otherwise pass unnoticed. Sonoluminescence is light produced by collapsing bubbles in liquid. In certain conditions, tiny bubbles in liquid can emit flashes of light when they collapse. This is called sonoluminescence. It occurs when sound waves create pressure variations in a liquid. The pressure causes bubbles to expand and contract rapidly. During the collapse, the gas inside the bubble is compressed so quickly that it heats to extreme temperatures, tens of thousands of degrees. This heat causes the gas to emit a brief flash of light, lasting only picoseconds. The exact mechanism is still not fully understood, and sonoluminescence remains a subject of research. It is one of the strangest ways light can be produced, emerging from sound and motion, a bridge between different forms of energy. The speed of light in a vacuum is a universal constant. The speed of light in a vacuum is always the same, roughly 300 million meters per second, no matter who measures it or how they are moving. This is one of the most fundamental principles of physics, a cornerstone of Einstein's theory of relativity. It means that if you are standing still and measure the speed of light, you get the same result as someone moving near the speed of light. This seems impossible, but it is true, and it has profound consequences. It means that time and space are not absolute. Time can slow down, and distances can contract, depending on how fast you are moving. It means that simultaneity is relative. Events that appear simultaneous to one observer may not be to another. The constancy of the speed of light reshapes our understanding of reality, showing that the universe is far stranger and more flexible than everyday experience suggests. Light carries information across vast distances. Every photon carries information about where it came from and what it encountered along the way. The wavelength tells you about the energy and temperature of the source. The intensity tells you how bright it was. The spectrum reveals composition. Polarization can indicate magnetic fields. Timing can reveal motion and structure. Astronomers gather photons from across the universe and decode them, reading stories written in light. A photon from a distant galaxy might have traveled for billions of years, carrying a snapshot of a time when the universe was young. Light from the sun takes 8 minutes to reach us, a real-time connection to our star. Light from the nearest stars takes years. Each photon is a messenger, and by collecting and studying these messengers, we piece together the history and nature of the cosmos. Light is not just what we see. It is how we know. Light has shaped human culture and imagination for millennia. From the earliest campfires to modern cities ablaze with neon and LED, light has been central to human experience. We worship the sun, fear the dark, and fill our nights with artificial glow. Light is a symbol, representing knowledge, purity, divinity, and hope. Darkness represents the unknown, danger, and ignorance. Cultures around the world celebrate festivals of light, from Diwali to Hanukkah to the winter solstice. Light guides travelers, marks sacred spaces, and illuminates art. The invention of the light bulb transformed society, extending the day and changing how we live and work. Light makes vision possible, and vision is our dominant sense. Most of what we know about the world comes from light. It is no wonder that light occupies such a profound place in our hearts and minds. It connects us to the universe, to each other, and to the flow of time itself. Shadows are the absence of light blocked by an object. A shadow is not a thing. It is the absence of light. When an opaque object blocks light, it creates a region where light cannot reach. This is a shadow. The sharpness of a shadow depends on the size and distance of the light source. A small, distant light, like the sun, creates sharp shadows with clear edges. A large, close light creates soft shadows with blurred edges. This blurring is called the penumbra, a region of partial shadow. Inside the umbra, the darkest part, light is completely blocked. Shadows change throughout the day as the sun moves across the sky. They lengthen at sunrise and sunset, shrink at noon. Ancient sundials used shadows to tell time, marking the passage of hours by the angle of the sun. Shadows also create depth and contrast, making it easier to see shapes and forms. Without shadows, the world would look flat and featureless. Shadows are silent partners to light, defining space and structure. Solar panels convert light into electricity through the photovoltaic effect. Solar panels capture light and turn it into electrical energy. They are made of semiconductor materials, usually silicon, that exhibit the photovoltaic effect. When light strikes the surface of the semiconductor, it knocks electrons loose from their atoms. These free electrons flow through the material, creating an electric current. The stronger the light, the more current is produced. Solar panels are a clean, renewable source of energy, converting sunlight directly into electricity without burning fuel or producing emissions. They are used to power homes, businesses, satellites, and remote devices. The efficiency of solar panels has improved dramatically over the decades, and they have become a key technology in the transition to sustainable energy. Every photon that strikes a solar panel carries energy, and the photovoltaic effect allows us to capture that energy and put it to use. It is light transformed, powering the modern world. Spectrometers split light into its component wavelengths for analysis. A spectrometer is an instrument that takes light and separates it into its constituent wavelengths, creating a spectrum. This can be done using a prism, a diffraction grating, or other optical elements. By analyzing the spectrum, scientists can determine the composition, temperature, density, and motion of the source. Spectrometers are used in astronomy to study stars, planets, and galaxies. They are used in chemistry to identify substances. They are used in environmental monitoring to detect pollutants. They are used in medicine to analyze blood and tissues. The spectrum is a fingerprint, unique to each element and molecule, and spectrometers decode that fingerprint. Some spectrometers cover visible light. Others extend into ultraviolet or infrared. Each wavelength carries information, and by spreading light into a spectrum, we reveal details that would be invisible otherwise. Spectrometry is one of the most powerful analytical tools ever developed, allowing us to see not just with light, but into it. Light can be used to cool atoms to near absolute zero. In a process called laser cooling, light can be used to slow down atoms, reducing their temperature to a fraction of a degree above absolute zero. This seems paradoxical, since light usually carries energy. But by carefully tuning the frequency of laser light, scientists can cause atoms to absorb photons in a way that opposes their motion. Each time an atom absorbs a photon, it slows down slightly. By hitting atoms from all directions with laser beams, they can be brought almost to a standstill. This creates ultra-cold gases where quantum effects dominate. At these temperatures, atoms behave in strange ways, forming exotic states of matter like Bose-Einstein condensates, where thousands of atoms act as a single quantum object. Laser cooling has opened up new frontiers in physics, allowing researchers to study quantum mechanics in unprecedented detail. It is a demonstration of how light, understood and controlled, can manipulate matter itself. Optical tweezers use focused light to trap and move tiny particles. Optical tweezers are devices that use a tightly focused laser beam to trap and manipulate microscopic objects. The light exerts a tiny force on particles, pulling them toward the focus of the beam. This force, called radiation pressure, is normally negligible, but when light is focused to a very small spot, the pressure becomes strong enough to hold particles in place. Optical tweezers can trap cells, bacteria, even individual molecules. Researchers use them to study biological processes, measure forces at the molecular level, and assemble tiny structures. The invention of optical tweezers earned a Nobel Prize in Physics in 2018. They are a tool of extraordinary precision, allowing scientists to manipulate the building blocks of life using nothing but light. It is a reminder that light, though intangible, has real, measurable effects on the physical world. Photons can become entangled, linking their properties across vast distances. Quantum entanglement is one of the strangest phenomena in physics. When two photons are entangled, they become connected in such a way that measuring the state of one instantly affects the state of the other, no matter how far apart they are. If you measure the polarization of one photon and find it vertical, the other will instantly have horizontal polarization, even if it is on the other side of the galaxy. This does not allow faster-than-light communication because the results are random until measured, but it does reveal a deep connection between particles. Einstein called it spooky action at a distance and was uncomfortable with it, but experiments have confirmed that entanglement is real. Entangled photons are used in quantum cryptography, creating communication systems that are theoretically impossible to eavesdrop on. They are also key to developing quantum computers, which could solve certain problems far faster than classical computers. Entanglement challenges our intuition about locality and separability, showing that the universe is interconnected in ways we are only beginning to understand. Light can be slowed to a near standstill in special materials. In a vacuum, light travels at its maximum speed. In ordinary materials, it slows down. But in certain exotic materials, light can be slowed to a crawl. Researchers have managed to slow light to just a few meters per second, slower than a walking pace, by passing it through ultra-cold clouds of atoms called Bose-Einstein condensates. These atoms are prepared in a special state where they interact strongly with light. As light enters, the atoms absorb and re-emit it in a coordinated way, creating a delay. The light is not destroyed. It is stored and released, moving through the medium at an extraordinarily slow speed. This research has potential applications in optical computing and communication, where controlling the speed of light could allow for better data storage and processing. Slowing light reveals the deep connection between light and matter, showing that light is not just a wave traveling through space, but something that interacts intimately with the material world. Light has been stopped completely and released again in laboratory experiments. In an even more extreme demonstration, scientists have stopped light entirely. By carefully preparing a cloud of ultra-cold atoms, they can cause incoming light to be absorbed in such a way that the information it carries is stored in the quantum state of the atoms. The light ceases to exist. Its energy and information are held in the atoms. Later, by changing the properties of the atoms, the light can be released again, emerging with the same properties it had before. This is called electromagnetically induced transparency. It is a technique that could be used to store quantum information or create delays in optical communication systems. The ability to stop and restart light challenges the idea that light must always be in motion. It blurs the line between light and matter, showing that under the right conditions, one can transform into the other. Holograms store three-dimensional information in patterns of light. Holograms are more than just pictures. They store a full three-dimensional representation of an object, encoded in an interference pattern. When you look at a traditional photograph, you see a flat image, a projection of 3 dimensions onto 2. When you look at a hologram, you see depth. You can move your head and see different perspectives, just as you would with a real object. This is possible because a hologram records not just the intensity of light, but also its phase, the position of the wave. The phase information encodes the three-dimensional structure. Creating a hologram requires coherent light, usually from a laser. The light is split into 2 beams. One reflects off the object, and the other serves as a reference. Where the 2 beams meet, they interfere, creating a pattern of light and dark. This pattern is recorded on a photographic plate. When the plate is later illuminated with similar light, it reconstructs the original wavefront, and you see a 3-dimensional image. Holograms are used for art, security, data storage, and research. They are a powerful demonstration of how light carries information in ways we are only beginning to fully exploit. The double-slit experiment reveals the wave-particle duality of light. One of the most famous experiments in physics is the double-slit experiment. Light is shone at a barrier with 2 narrow slits. On the far side, a screen records where the light lands. If light were made of particles, you would expect 2 bright lines on the screen, one behind each slit. But that is not what happens. Instead, you see an interference pattern, alternating bands of light and dark. This is the signature of waves. Light passing through both slits interferes with itself, creating regions of constructive and destructive interference. But here is the strange part. If you send photons through one at a time, the pattern still builds up. Each photon seems to interfere with itself, as if it passes through both slits at once. But if you try to measure which slit the photon goes through, the interference pattern disappears, and you get 2 bright lines. The act of measurement changes the outcome. This experiment reveals the dual nature of light, behaving as both wave and particle, depending on how you observe it. It is a cornerstone of quantum mechanics, and a reminder that reality at small scales is profoundly strange. Interferometers measure tiny changes by comparing light waves. An interferometer is an instrument that uses the interference of light waves to make incredibly precise measurements. Light is split into two beams that travel different paths. When they are recombined, they interfere. If the paths are exactly the same length, the waves add together and you see bright light. If one path is even slightly longer, the waves arrive out of phase and interfere destructively, creating darkness. By observing the interference pattern, you can detect changes in path length far smaller than the wavelength of light. Interferometers are used in many applications. They measure the flatness of mirrors and lenses to nanometer precision. They detect gravitational waves, tiny ripples in spacetime caused by colliding black holes and neutron stars. They study the atmosphere, tracking changes in density and temperature. They are essential tools in physics, astronomy, and engineering. The sensitivity of interferometers comes from the wave nature of light. Waves carry information in their phase, and by comparing phases, interferometers can detect changes invisible to any other instrument. LIGO detected gravitational waves using laser interferometry. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is one of the most sensitive instruments ever built. It consists of two facilities, one in Washington and one in Louisiana, each with two arms stretching 4 kilometers in opposite directions. Laser light is split and sent down each arm, bouncing off mirrors at the ends before recombining. Under normal conditions, the light returns in phase and interferes constructively. But when a gravitational wave passes through, it stretches space in one direction and compresses it in the other. This changes the length of the arms by an incredibly tiny amount, less than the width of a proton. This tiny change shifts the phase of the light, creating an interference pattern that LIGO can detect. In 2015, LIGO made the first direct detection of gravitational waves, caused by two black holes spiraling together and merging over 1 billion light-years away. It was a triumph of physics and engineering, confirming a prediction of general relativity and opening a new way to observe the universe. LIGO uses light to sense distortions in space itself. Photography captures moments by recording patterns of light on a sensor. Photography is the art and science of capturing light. Early cameras used chemical processes. Light entering the camera exposed a film coated with silver compounds. Where light struck, the chemicals changed, creating a latent image. Developing the film made the image visible and permanent. The longer the exposure, the more light was captured, allowing photographers to record everything from bright daylight scenes to faint stars. Modern cameras use digital sensors made of millions of light-sensitive pixels. Each pixel converts incoming photons into an electrical signal, which is stored as data. The camera's processor interprets this data to create an image. Adjusting the aperture controls how much light enters. Adjusting the shutter speed controls how long the sensor is exposed. Adjusting the ISO changes the sensitivity. Together, these settings allow photographers to freeze motion, blur movement, isolate subjects, and create artistic effects. Photography is a form of writing with light, preserving moments that would otherwise be lost. Long exposure photography can reveal invisible details in the night sky. By leaving a camera's shutter open for minutes or even hours, photographers can capture light too faint for the eye to see. Stars that appear as single points to the unaided eye reveal their colors. The Milky Way emerges in vivid detail. Faint nebulae glow softly. Meteor showers leave streaks across the frame. Star trails, long arcs tracing the rotation of the Earth, appear as the stars seem to circle the pole. Long exposures accumulate photons, building up an image that reveals the hidden richness of the night. This technique is used by astronomers to photograph distant galaxies and faint celestial objects. It turns the camera into a time machine, gathering light that has traveled for millions or billions of years. Long exposure photography shows that there is far more to see than meets the eye. The universe is luminous, if only we give ourselves time to look. Bioluminescent organisms create light without heat. In the depths of the ocean, in caves, and in forests, certain organisms produce light through biochemical reactions. This light is cold, produced without the heat that comes from burning or incandescence. Bioluminescence has evolved independently in many lineages, suggesting it offers significant advantages. In the ocean, bioluminescence is common. Fish, jellyfish, squid, and plankton all use it. Some use it to attract prey, dangling, glowing lures. Others use it to startle predators or create decoys. Some use it to communicate, flashing patterns to find mates or coordinate behavior. On land, fireflies are the most familiar example. They flash in species-specific patterns, males signaling to females. Some fungi glow in the dark, emitting a faint green light. The purpose is unclear, though it may attract insects that disperse spores. Bioluminescence is beautiful and efficient. It converts chemical energy directly into light with almost no waste heat. Scientists study it to develop new imaging techniques and biosensors. The chemistry of bioluminescence is a natural wonder, a reminder that light can emerge from life itself. Chemiluminescence produces light through chemical reactions. Similar to bioluminescence, chemiluminescence is the production of light from a chemical reaction, but it occurs outside living organisms. Glow sticks are a common example. When you bend a glow stick, you break a small vial inside, mixing two chemicals. The reaction between them produces light without heat. The color depends on the specific chemicals and dyes used. Chemiluminescence is used in emergency lighting, forensics, and scientific research. Luminol, a chemical that glows blue when it reacts with blood, is used at crime scenes to reveal traces invisible under normal light. Chemiluminescence is a demonstration of how energy stored in chemical bonds can be released as light. It is cold light, efficient and controllable, a tool for both science and everyday use. Sunlight drives the water cycle by evaporating water. The sun powers the movement of water across Earth. Sunlight warms the surface of oceans, lakes, and rivers, providing the energy needed to evaporate water. Water molecules absorb energy and break free from the liquid, becoming vapor. This vapor rises into the atmosphere, cools, and condenses into clouds. Eventually, it falls back to the surface as rain or snow, completing the cycle. Without sunlight, the water cycle would not exist. The energy from light is what lifts water into the sky and drives weather patterns. Hurricanes, thunderstorms, and gentle rains all trace their energy back to the sun. The water cycle is a global engine, distributing heat and moisture, shaping climates, and sustaining life. Light is the fuel, invisible but essential. Light pressure from the sun pushes comet tails away. Comets are icy bodies that orbit the sun. As they approach, the sun's heat causes ice to vaporize, creating a glowing coma of gas and dust around the nucleus. This material streams away from the comet, forming tails. Comets can have two tails: a dust tail made of solid particles pushed by solar wind, and an ion tail made of charged gas pushed by light itself. Photons from the sun strike dust particles and exert a tiny force called radiation pressure. Over time, this pressure pushes the dust away from the sun, creating a tail that always points away from the sun, regardless of the comet's direction of travel. The ion tail is even more directly influenced by light and the solar wind, often appearing blue due to ionized gases. Comet tails are visible evidence that light carries momentum, that even massless photons can push matter. Stars produce different colors based on their temperature. Stars come in many colors, from deep red to brilliant blue. This color is determined primarily by temperature. Cooler stars emit more red light. Hotter stars emit more blue light. This relationship is described by a principle called blackbody radiation. A perfect blackbody is an object that absorbs all light and re-emits it based solely on temperature. Stars approximate blackbodies. A star with a surface temperature around 3000 degrees Celsius glows red. A star at 6000 degrees appears yellow-white, like our Sun. A star at 10,000 degrees or more shines blue. By measuring a star's color, astronomers can estimate its temperature. Color also correlates with other properties. Blue stars are typically massive and short-lived. Red stars are often smaller and can burn for trillions of years. The color of a star tells a story about its life, its past, and its future. Brown dwarfs are failed stars that glow faintly in infrared. Brown dwarfs are objects too massive to be planets, but not massive enough to sustain hydrogen fusion like stars. They form like stars from collapsing clouds of gas, but they never ignite. Without fusion, they do not shine brightly like stars. Instead, they glow faintly in infrared, radiating the heat left over from their formation and the slow fusion of deuterium, a heavier form of hydrogen. Brown dwarfs are dim and hard to detect. Most of the light they emit is invisible to human eyes, but infrared telescopes can see them. They occupy a twilight zone between planets and stars, objects in their own category. Studying brown dwarfs helps astronomers understand the process of star formation and the minimum mass required for fusion. They are also interesting in their own right, strange worlds with atmospheres, weather, and possibly even moons. White dwarfs are the remnants of stars that have exhausted their fuel. When a star like the Sun exhausts its nuclear fuel, it swells into a red giant and then sheds its outer layers. What remains is the core, a dense, hot object called a white dwarf. White dwarfs are incredibly dense. A teaspoon of white dwarf material would weigh several tons. They no longer produce energy through fusion. Instead, they shine by radiating stored heat. Over billions of years, they cool and fade, eventually becoming black dwarfs, though the universe is not old enough for any black dwarfs to exist yet. White dwarfs are held up not by thermal pressure, as in normal stars, but by quantum pressure from electrons packed tightly together. This pressure has a limit, called the Chandrasekhar limit. If a white dwarf gains too much mass, it can no longer support itself and collapses, often triggering a supernova explosion. White dwarfs are the fate of most stars, including our Sun, quiet endings to billions of years of light. Neutron stars are so dense that light bends noticeably around them. Neutron stars are the collapsed cores of massive stars that exploded as supernovae. They are incredibly dense, packing more mass than the Sun into a sphere just 20 kilometers across. A teaspoon of neutron star material would weigh 1 billion tons. The gravity near a neutron star is so strong that it bends space significantly. Light traveling near a neutron star follows a curved path. If you could stand on the surface, you would see light from the back of the star bent around and visible above the horizon. Neutron stars also spin rapidly, sometimes hundreds of times per second. Some emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like a lighthouse. If the beam points toward Earth, we see regular pulses of light. These are called pulsars. Pulsars are among the most precise clocks in the universe, their pulses timed to fractions of a second. Neutron stars are laboratories for extreme physics, where gravity, density, and magnetism reach levels impossible to replicate on Earth. Supernovae are among the brightest events in the universe. When a massive star exhausts its fuel, it can no longer support itself against gravity. The core collapses in a fraction of a second, triggering a catastrophic explosion called a supernova. For a few weeks, a single supernova can outshine an entire galaxy. The explosion releases an immense amount of energy, much of it in the form of light. Supernovae produce elements heavier than iron, which cannot be made in normal stellar fusion. These elements are blasted into space, enriching the interstellar medium and providing the raw material for new stars and planets. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in supernovae. Supernovae also leave behind remnants, expanding shells of gas, and, at the center, either a neutron star or a black hole. They are among the most energetic events in the universe, and their light carries news of stellar death across the cosmos. Gamma-ray bursts are the most energetic explosions since the Big Bang. Gamma-ray bursts are brief but incredibly powerful flashes of gamma rays, the highest energy form of light. They last from milliseconds to minutes, but release more energy than the sun will emit in its entire lifetime. Gamma-ray bursts are thought to occur when massive stars collapse into black holes or when neutron stars collide. The collapse creates jets of particles moving near the speed of light. These jets emit intense gamma rays. If a jet points toward Earth, we see a gamma-ray burst. Most bursts come from distant galaxies, billions of light-years away. Despite the distance, they are detectable, a testament to their power. After the initial burst, an afterglow appears, visible in X-rays, ultraviolet, and optical light. This afterglow can last for days or weeks, allowing astronomers to study the event in detail. Gamma-ray bursts are extreme, violent, and fascinating, pushing the boundaries of what we understand about light and energy. The color of a flame reveals the chemicals burning. When something burns, it emits light. The color of that light depends on what is burning and at what temperature. A simple campfire burns wood and appears orange or yellow, a sign of soot particles heated to incandescence. But if you add certain chemicals, the color changes. Copper compounds burn green. Strontium burns red. Barium burns green. Sodium burns bright yellow. These colors come from excited electrons in the atoms. Heat from the flame raises electrons to higher energy levels. When they fall back down, they release light at specific wavelengths. Each element has a unique set of wavelengths, a spectral fingerprint. Fireworks use this principle, adding metal salts to create brilliant colors in the sky. Flame tests are also used in chemistry to identify elements. By observing the color of a flame, you can determine what is burning. It is a direct link between light and matter, a window into the atomic world. The Doppler effect shifts the frequency of light from moving objects. Just as the pitch of a siren changes as it passes you, the frequency of light changes depending on the motion of the source. If a light source moves toward you, the light waves are compressed, increasing the frequency and shifting the color toward blue. If it moves away, the waves are stretched, decreasing the frequency and shifting toward red. This is the Doppler effect. Astronomers use it to measure the motion of stars, galaxies, and planets. A star moving toward us shows a blue shift in its spectrum. A star moving away shows a red shift. By measuring these shifts, astronomers can determine velocities with great precision. The Doppler effect is also used to detect exoplanets. As a planet orbits a star, the star wobbles slightly. This wobble causes tiny shifts in the star's light. By detecting these shifts, astronomers can infer the presence of a planet, even if they cannot see it directly. The Doppler effect turns light into a tool for measuring motion. Lasers are used to measure distances with extreme precision. Lasers can measure distances by timing how long it takes light to travel. A laser pulse is sent toward a target, and a detector measures when the reflection returns. Since the speed of light is known, the distance can be calculated. This technique called laser ranging, is used in many applications. Surveyors use it to measure land. Archaeologists use it to map ruins. Autonomous cars use it to detect obstacles. Laser ranging is also used in space. Reflectors left on the moon by Apollo astronauts allow scientists to measure the distance to the moon to within a few centimeters. Over decades of measurements, this has revealed that the moon is slowly drifting away from Earth at about 4 centimeters per year. Laser ranging is a demonstration of how light, understood and controlled, becomes a tool of extraordinary precision. Light can reveal hidden writing and artworks. Infrared and ultraviolet light can reveal details invisible under normal light. Art conservators use infrared to see underdrawings beneath paintings, sketches made by the artist before applying paint. Ultraviolet light can reveal overpainting, repairs, and alterations. It can also detect invisible inks and hidden signatures. Forensic scientists use similar techniques to read erased or obscured text, to detect forged documents, and to analyze crime scenes. Different materials absorb and reflect different wavelengths, and by illuminating an object with specific types of light, hidden details emerge. Multispectral imaging, which captures images at many wavelengths, has been used to read ancient texts that are too faded or damaged to read with the naked eye. Light reveals what is hidden, not by magic, but by science, by understanding how materials interact with different wavelengths. Refraction makes underwater objects appear closer than they are. When you look at something underwater, it appears closer to the surface than it actually is. This is caused by refraction. Light from the object bends as it exits the water and enters the air. Your brain assumes light travels in straight lines, so it interprets the bent light as coming from a shallower location. This can be disorienting for divers and spearfishers, who must learn to compensate. The same principle makes a straw in a glass of water look broken at the surface. The light from the submerged part bends as it leaves the water, creating a visual discontinuity. Refraction is also why pools look shallower than they are, a potential danger for those who cannot swim. Understanding refraction helps us interpret what we see and build devices like underwater cameras and goggles that correct for the distortion. Dispersion creates the spectrum of a rainbow. When white light enters a raindrop, it slows down and bends. Different colors bend by different amounts, separating the light into a spectrum. Red bends the least, violet the most. Inside the droplet, the light reflects off the back surface. Then, as it exits, it bends again, spreading the colors further. Each droplet disperses light, but only one color from each droplet reaches your eye, depending on the droplet's position relative to the sun and your line of sight. Millions of droplets together create the continuous arc of a rainbow, each contributing a different color. The same principle explains the colors in prisms, oil slicks, and soap bubbles. Dispersion is a consequence of the fact that the speed of light in a material depends on wavelength. It is a beautiful reminder that white light is not simple but composite, a blend of many colors waiting to be revealed. Optical fibers allow surgeons to see inside the body. Fiber optic technology is not just for communication. It is also used in medicine. Endoscopes are flexible tubes containing bundles of optical fibers. Light is sent down some fibers to illuminate the inside of the body. Other fibers carry the reflected light back, creating an image. This allows doctors to see inside the stomach, lungs, joints, and other areas without major surgery. Modern endoscopes also include tiny cameras and tools, allowing for minimally invasive procedures. Fiber optics have revolutionized medicine, making diagnosis and treatment safer and less traumatic for patients. Light, guided through thin strands of glass, becomes a window into the living body, revealing what was once hidden. Thermal imaging cameras detect infrared light emitted by warm objects. Everything with temperature emits infrared radiation. The warmer an object, the more infrared it emits. Thermal imaging cameras detect this radiation and convert it into a visible image, with different colors representing different temperatures. Warm areas appear red or white. Cool areas appear blue or black. Thermal cameras are used in many fields. Firefighters use them to see through smoke. Search and rescue teams use them to find people in darkness. Energy auditors use them to detect heat leaks in buildings. Wildlife researchers use them to observe animals at night. Thermal imaging is also used in medicine to detect inflammation and poor circulation. Because thermal cameras see infrared light, they can operate in complete darkness. They reveal a hidden world of heat, making the invisible visible. Streetlights use different technologies to produce light efficiently. Streetlights have evolved over the years. Early streetlights used gas flames, then incandescent bulbs. Later, high-pressure sodium lamps became common. These produce a distinctive orange-yellow light by exciting sodium vapor. They are efficient but render colors poorly because they emit light in a narrow range of wavelengths. Mercury vapor lamps produce a bluish-white light and were also widely used. Today, many cities are switching to LED streetlights. LEDs are more efficient, longer-lasting, and can produce a range of colors. They also allow for better control, enabling smart lighting systems that adjust brightness based on need. The color and quality of streetlights affect not just visibility, but also safety, mood, and even wildlife. Choosing the right light source is a balance between efficiency, color quality, and environmental impact. Stained glass windows create color by absorbing certain wavelengths. Stained glass windows have adorned churches and buildings for centuries. They create vivid colors not through pigments painted on the surface, but through the glass itself. Metal oxides are added to molten glass during production. Cobalt produces deep blue. Gold creates red or purple. Copper makes green or blue. These metals absorb certain wavelengths of light and allow others to pass through. When sunlight shines through stained glass, some colors are filtered out and others pass through, creating brilliant hues. The effect changes with the angle and intensity of sunlight, making the windows dynamic and alive. Stained glass is both art and science, a collaboration between human creativity and the physics of light. Aurora light shows vary in color based on altitude and atmospheric gases. Auroras occur when charged particles from the sun collide with atoms in Earth's atmosphere. The color of the aurora depends on which atoms are struck and at what altitude. At high altitudes, around 200 to 300 kilometers, oxygen emits red light. At lower altitudes, around 100 to 200 kilometers, oxygen emits green, the most common aurora color. Nitrogen produces blue or purple light, especially at the lower edges of auroras. The intensity and color of an aurora can change within minutes as the solar wind fluctuates and particles hit different layers of the atmosphere. Auroras are dynamic, shifting curtains of light, a visible interaction between the sun and Earth. Moonbows are rainbows created by moonlight instead of sunlight. Just as sunlight can create rainbows, so can moonlight. Moonbows, also called lunar rainbows, form when moonlight refracts through raindrops. They are much fainter than daytime rainbows because moonlight is much dimmer than sunlight. Often, they appear nearly white to the human eye, though long exposure photography can reveal their colors. Moonbows are most commonly seen near waterfalls, where mist provides the necessary water droplets, and during full moons when the light is brightest, they are rare and ethereal, a reminder that the principles of light apply day and night. Iridescence in butterfly wings comes from microscopic structures, not pigments. Some butterflies display brilliant, shimmering colors that change depending on the viewing angle. These colors are not created by pigments, but by the physical structure of the wing scales. The scales contain layers of microscopic ridges and grooves that reflect light. When light waves reflect off these structures, they interfere with each other. Depending on the thickness and spacing of the layers, certain wavelengths interfere constructively and are enhanced, while others interfere destructively and are suppressed. The result is vivid, iridescent color. Because the interference depends on angle, the color shifts as you move. This is called structural coloration. It is also seen in peacock feathers, beetle shells, and soap bubbles. Structural coloration is more durable than pigment-based color and can produce hues that pigments cannot match. Opal gemstones display color through diffraction of light. Opals are unique gemstones that display a play of colors unlike any other stone. This effect, called opalescence, is caused by the internal structure of the opal. Opals are made of tiny silica spheres arranged in a regular pattern. Light entering the opal diffracts as it interacts with these spheres. Different wavelengths diffract by different amounts, separating white light into a spectrum of colors. The size and arrangement of the spheres determine which colors appear. As you move the opal, the colors shift and change, creating a dynamic, fiery display. Opals demonstrate how structure at the microscopic level can manipulate light to create beauty. Mirages in the desert are caused by temperature gradients bending light. In deserts and on hot roads, mirages create the illusion of water shimmering in the distance. This happens because the air near the ground is much hotter than the air above. Light traveling from the sky toward the ground bends as it passes through these layers of different temperature and density. At shallow angles, the light bends so much that it curves upward before reaching the ground. Your brain interprets this as a reflection, as if light were bouncing off a water surface. As you approach, the mirage retreats. You never reach it because it is not a place, but an optical effect. Mirages are real phenomena, light behaving predictably in response to the environment. Light exhibits diffraction when it passes through narrow slits or around edges. Diffraction is the bending and spreading of light as it encounters obstacles or openings. When light passes through a narrow slit, it does not simply continue in a straight line. It spreads out, creating a pattern of light and dark bands. This is because different parts of the wavefront travel slightly different distances, and they interfere with each other. Diffraction is most noticeable when the size of the obstacle or opening is comparable to the wavelength of light. It is why you can hear sound around corners, but cannot see around them easily. Sound has much longer wavelengths. Diffraction limits the resolution of optical instruments. No matter how perfect a telescope or microscope, it cannot resolve details smaller than about half the wavelength of light used. Diffraction is a fundamental property of waves, a reminder that light does not always travel in straight lines. The colors of a sunset can be enhanced by particles in the atmosphere. Dust, smoke, and pollution can affect the colors of a sunset. Large particles scatter light differently than air molecules. They tend to scatter longer wavelengths more than shorter ones, intensifying reds and oranges. This is why sunsets after volcanic eruptions or forest fires can be especially vivid. Ash and aerosols spread through the atmosphere, enriching the colors for months. While pollution is harmful, it does create visually striking sunsets, a side effect of particles interacting with light. The color of the sky is always a product of what is in it, a reflection of the atmosphere's composition. Different types of light bulbs have different color temperatures. Light from a candle appears warm and orange. Light from an overcast sky appears cool and blue. This difference is described by color temperature, measured in Kelvin. Lower temperatures correspond to warmer, redder light. Higher temperatures correspond to cooler, bluer light. An incandescent bulb has a color temperature around 2700 Kelvin, producing warm, yellowish light. A fluorescent bulb might be 4000 Kelvin, producing neutral white light. Daylight is around 5500 to 6500 Kelvin. LED bulbs can be manufactured to produce a range of color temperatures from warm to cool. Color temperature affects mood and perception. Warm light feels cozy and intimate. Cool light feels bright and alert. Choosing the right color temperature is an important part of lighting design. Shadows can have colored edges due to diffraction. When light passes around an object, it diffracts, bending slightly into the shadow region. This creates a fuzzy edge rather than a sharp boundary. If the light source is not monochromatic, different colors diffract by different amounts, and you can see faint colored fringes along the edge of a shadow. This effect is subtle and usually requires careful observation or magnification to see. It is a reminder that even shadows, the absence of light, are shaped by the wave nature of light. Light can exert force and move objects. Radiation pressure, the force exerted by light, is real. When photons strike a surface, they transfer momentum. For everyday objects, this force is negligible, but for very light objects in space, it can be significant. Solar sails use radiation pressure from the sun to propel spacecraft. A large, reflective sail catches photons, and over time, the accumulated momentum accelerates the spacecraft. No fuel is needed, just sunlight. Radiation pressure also affects comets, pushing dust and gas away from the sun to form tails. In laboratories, optical tweezers use focused laser beams to trap and manipulate tiny particles, including living cells. Light, though intangible, has physical effects, a bridge between energy and matter. Sunlight is essential for vitamin D production in human skin. When ultraviolet B radiation from the sun strikes your skin, it triggers a chemical reaction that produces vitamin D. This vitamin is essential for bone health, immune function, and many other processes. Without adequate sunlight, people can develop vitamin D deficiency, leading to problems like rickets in children and osteoporosis in adults. This is why moderate sun exposure is important, especially in regions with long winters or limited sunlight. However, too much ultraviolet exposure increases the risk of skin cancer, so balance is key. Sunlight, in the right amounts, is necessary for health, another way light sustains life. Circadian rhythms are regulated by exposure to light. Your body has an internal clock that regulates sleep, wakefulness, and many physiological processes. This clock is synchronized by light. Exposure to bright light, especially blue light, in the morning, signals your brain that it is daytime. This suppresses the production of melatonin, a hormone that makes you sleepy and increases alertness. In the evening, as light fades, melatonin production increases, preparing you for sleep. Artificial light, especially from screens, can disrupt this rhythm by signaling daytime when it is night. This can lead to sleep problems and other health issues. Understanding the role of light in regulating circadian rhythms has led to recommendations like reducing screen time before bed and using warmer, dimmer lights in the evening. Light is not just something we see. It is a biological signal that shapes our daily lives. Fireflies synchronize their flashes using light signals. In some species of fireflies, individuals synchronize their flashing, creating waves of light that ripple through forests. Each firefly adjusts its timing based on the flashes it sees from neighbors. This emergent behavior creates spectacular displays where thousands of fireflies blink in unison. The mechanism is simple but elegant. Each firefly has an internal oscillator that controls its flash. When it sees a flash from another firefly, it adjusts its own timing slightly. Over time, the population synchronizes. Scientists study firefly synchronization to understand collective behavior and self-organization. It is a natural example of how simple rules and communication through light can create complex, coordinated patterns. Light allows plants to orient themselves toward the sun. Plants exhibit a behavior called phototropism, where they grow toward light. This is controlled by hormones that accumulate on the shaded side of the stem, causing cells there to elongate more than those on the light side. The result is that the stem bends toward the light. This ensures that leaves receive maximum sunlight for photosynthesis. Roots, in contrast, often exhibit negative phototropism, growing away from light and into the soil. Light is a cue that helps plants navigate their environment, optimizing their position for growth and survival. The speed of light was first measured accurately in the 1600s. The speed of light is so fast that measuring it was a challenge for early scientists. In 1676, Danish astronomer Ole Rømer made the first quantitative estimate. He observed the moons of Jupiter and noticed that the timing of their eclipses changed depending on Earth's position in its orbit. When Earth was farther from Jupiter, the eclipses appeared to happen later. Rømer realized this was because light took time to travel the extra distance. His estimate was not exact, but it was remarkably close. Later, more precise measurements were made using rotating mirrors and other techniques. In 1879, Albert Michelson measured the speed of light to great accuracy, and his work laid the foundation for modern physics. Today, the speed of light is defined as exactly 299,792,458 meters per second, and the meter is defined based on that speed. Photons have zero rest mass, but possess energy and momentum. Photons are strange particles. They have no mass, at least not in the traditional sense. If a photon were to stop, it would cease to exist. Photons always move at the speed of light. Despite having no mass, they carry energy and momentum. The energy of a photon is proportional to its frequency. High-frequency light, like ultraviolet or X-rays, carries more energy per photon than low-frequency light, like infrared or radio waves. The momentum of a photon, though small, is real and measurable. This is why light can exert pressure, and why photons can transfer momentum to atoms and molecules. The dual nature of photons, behaving as both waves and particles, is central to quantum mechanics and our understanding of the universe. Gravitational lensing has been used to discover distant galaxies. Massive objects like galaxy clusters warp space, and this warping bends the path of light from objects behind them. This creates gravitational lenses that can magnify and distort distant galaxies, making them visible when they would otherwise be too faint to detect. Gravitational lensing has allowed astronomers to study galaxies from the early universe, revealing how galaxies formed and evolved. It has also been used to map the distribution of dark matter, the invisible substance that makes up most of the mass in the universe. Dark matter does not emit light, but it does bend it, and by studying how light is lensed, scientists can infer where dark matter is. Gravitational lensing turns the universe into a natural telescope, using gravity to magnify the distant and faint. Black body radiation describes how objects emit light based on temperature. Every object with temperature emits electromagnetic radiation. The spectrum of this radiation depends only on the object's temperature. A perfect black body absorbs all incoming light and re-emits it based solely on its temperature. Real objects approximate this behavior. As temperature increases, the peak of the emission shifts to shorter wavelengths. A cool object emits mostly infrared. As it heats, it glows red, then orange, then white, and finally blue. This is described by Planck's law, which was developed in the early 1900s and marked the beginning of quantum mechanics. Black body radiation explains why stars of different temperatures have different colors and why heated metal glows. It is a fundamental link between temperature and light. Wien's law relates the peak wavelength of light to the temperature of the source. Wien's law is a simple formula that tells you the wavelength at which an object emits the most light based on its temperature. As temperature increases, the peak wavelength decreases. A cool star emits most of its light in the infrared. A hot star emits most of its light in the ultraviolet. Our Sun, with a surface temperature around 5,500 Kelvin, emits most of its light in the yellow-green part of the spectrum, which is not a coincidence. Our eyes evolved to be most sensitive to the wavelengths where the Sun emits the most light. Wien's law is a tool astronomers use to estimate the temperature of stars and other objects just by observing their color. The Stefan Boltzmann law relates an object's temperature to the total energy it radiates. The Stefan Boltzmann law states that the total energy radiated by an object increases with the fourth power of its temperature. Double the temperature, and the object radiates 16 times more energy. This law explains why hot objects shine so brightly. A small increase in temperature leads to a large increase in radiated energy. It applies to stars, planets, and everyday objects. It is why the Sun, though only moderately hotter than a campfire in absolute terms, radiates an incomprehensible amount of energy. It is also why cooling systems are so important in electronics. As components heat up, they radiate energy, and managing that heat is essential for performance and safety. Light from the Big Bang still fills the universe as the cosmic microwave background. About 13.8 billion years ago, the universe began in an event called the Big Bang. In its earliest moments, the universe was incredibly hot and dense, filled with a plasma of particles and radiation. As the universe expanded and cooled, particles combined to form neutral atoms. At that moment, light that had been trapped suddenly became free to travel. That light has been traveling ever since, stretched by the expansion of the universe into microwaves. Today, it fills the entire universe as a faint glow called the cosmic microwave background, or CMB. Telescopes tuned to microwave frequencies can detect it. The CMB is remarkably uniform, but it has tiny fluctuations, and these fluctuations reveal the seeds of galaxies and the structure of the universe. The CMB is a snapshot of the universe when it was only 380,000 years old, a relic of creation itself, visible as light. Photons from the Sun take thousands of years to travel from the core to the surface. Nuclear fusion in the Sun's core produces photons, packets of light energy. But the core is incredibly dense, and photons cannot travel far before being absorbed and re-emitted by an atom. Each time a photon is absorbed, it transfers energy, and a new photon is emitted in a random direction. This process, called a random walk, means that a photon bounces around inside the Sun for a very long time before reaching the surface. Estimates suggest it takes tens of thousands to hundreds of thousands of years for energy produced in the core to make the journey to the surface. Once it reaches the surface, it escapes into space as sunlight and travels to Earth in just 8 minutes. The light you see from the Sun today began its journey in the Sun's core long before human civilization existed. Lasers can cut through metal by focusing intense light energy. Lasers concentrate light into a very small area, delivering enormous amounts of energy. When a laser beam strikes metal, the energy heats the metal to its melting or boiling point. The material vaporizes or melts away, creating a cut. Laser cutting is precise and clean, used in manufacturing, surgery, and art. Different types of lasers are used for different materials. CO2 lasers are common for cutting and engraving. Fiber lasers are used for metals. The power of a laser comes from its coherence and focus. All the light waves are synchronized and concentrated, creating a tool that can cut, weld, and even drill through materials with incredible precision. Sundials use shadows cast by sunlight to tell time. A sundial is one of the oldest timekeeping devices. It consists of a flat surface with markings and a raised object called a gnomon. As the sun moves across the sky, the gnomon casts a shadow on the surface. The position of the shadow changes with the time of day. By marking the surface with hours, you can read the time from the shadow's position. Sundials are beautifully simple, requiring no power or mechanism. They work because the sun's path is predictable and regular. However, they only work when the sun is shining, and they need to be calibrated for the specific latitude where they are used. Sundials are a direct application of light and shadow to measure time, connecting us to the rhythms of the sun. Light pollution affects animal migration and behavior. Many animals rely on natural light cues to navigate, hunt, and reproduce. Sea turtles, for example, hatch at night and instinctively move toward the brightest horizon, which naturally is the ocean reflecting moonlight. Artificial lights from buildings and roads can disorient them, leading hatchlings away from the sea. Migratory birds use stars for navigation, and city lights can confuse them, causing collisions with buildings. Nocturnal animals that hunt or forage at night are disrupted by constant artificial light. Even insects are affected. Moths and other insects are drawn to lights, exhausting themselves and becoming easy prey. Light pollution is an unintended consequence of human development, and addressing it requires thoughtful lighting design that minimizes impact on wildlife. Transparent materials allow light to pass through with minimal scattering. Glass, water, and air are transparent because their molecular structure does not significantly scatter or absorb visible light. Light waves pass through with little interaction. Transparency depends on wavelength. Glass is transparent to visible light but opaque to ultraviolet. Water is transparent to visible light but absorbs infrared. Transparency is not absolute. Even clear materials absorb some light, which is why very thick glass appears slightly greenish. Transparency is a valuable property, enabling windows, lenses, and optical fibers. Understanding what makes materials transparent has led to innovations in optics and materials science. Translucent materials scatter light, allowing it to pass, but blurring images. Translucent materials, like frosted glass or wax paper, allow light through, but scatter it, preventing clear images from forming. The scattering occurs because the material has irregularities, or particles that deflect light in many directions. This diffuses the light, softening it and reducing glare. Translucent materials are used in lampshades, privacy windows, and diffusers for photography. They control light without blocking it entirely, creating a soft, even glow. Translucency is a middle ground between transparency and opacity. Opaque materials block light entirely. Opaque materials absorb or reflect all incoming light. None passes through. Metals are typically opaque because free electrons absorb light across the visible spectrum. Wood, stone, and most solids are opaque due to their structure and composition. Opacity is essential for creating shadows, blocking unwanted light, and controlling illumination. Blackout curtains, walls, and barriers all rely on opacity. The degree of opacity can vary. Some materials are more opaque than others, and thin layers of an opaque material may allow some light through if the layer is thin enough. Opacity is a fundamental optical property, as important as transparency in shaping how we use light. Brewster's angle is the angle at which reflected light is completely polarized. When light reflects off a surface, it can become partially polarized. At a specific angle, called Brewster's angle, the reflected light is completely polarized. This angle depends on the refractive indices of the two materials. For light reflecting off water or glass, Brewster's angle is around 56 degrees. At this angle, only light polarized parallel to the surface is reflected. Light polarized perpendicular to the surface is refracted into the material. Photographers use polarizing filters to eliminate reflections from water or glass by aligning the filter to block light polarized at Brewster's angle. Brewster's angle is a precise relationship, a mathematical description of how light and materials interact. Snell's law describes how light bends when it enters a new material. Snell's law is a simple equation that predicts the angle of refraction when light passes from one material to another. It relates the angle of incidence, the angle of refraction, and the refractive indices of the two materials. Snell's law is fundamental to optics. It is used to design lenses, prisms, and optical instruments. It explains why a straw looks bent in water and why mirages appear on hot roads. Snell's law shows that light bends in predictable, calculable ways, turning refraction from an observation into a tool. The critical angle is the angle beyond which total internal reflection occurs. When light travels from a denser material to a less dense one, there is an angle, called the critical angle, beyond which no light escapes. Instead, all the light reflects back into the denser material. This is total internal reflection. It is the principle behind fiber optics, where light is trapped inside a glass fiber and travels along it without escaping. Diamonds have a small critical angle, which means light entering a diamond bounces around inside many times before escaping. This is part of what gives diamonds their brilliance. Total internal reflection is a boundary phenomenon, a point where refraction gives way to reflection. Prisms can be used to change the direction of light without dispersion. While prisms are famous for splitting light into a spectrum, they can also redirect light without separating colors. By using the right angles and materials, prisms can reflect light internally or bend it without significant dispersion. Binoculars and periscopes use prisms to fold the path of light, making the device more compact. Prisms are versatile optical components used for steering, inverting, and manipulating light in precise ways. Scattering makes the sky appear blue and sunsets appear red. Scattering is the process by which light is redirected by particles or molecules. The amount of scattering depends on wavelength. Shorter wavelengths scatter more than longer ones. This is why the sky is blue. Blue light from the sun scatters in all directions, filling the sky with blue light. At sunset, sunlight passes through more atmosphere, and most of the blue light has scattered away, leaving red and orange to dominate. Scattering explains not just the color of the sky, but also the appearance of distant mountains, the glow of twilight, and the way fog diffuses light. It is a key process in atmospheric optics. The horizon appears to glow at sunset due to scattering in the atmosphere. Even after the sun has set below the horizon, the sky remains bright for a while. This is twilight, caused by sunlight scattering off the upper atmosphere. There are three types of twilight. Civil twilight, when the sun is just below the horizon and the sky is still bright enough to see clearly. Nautical twilight, when the horizon is still visible but it is darker. Astronomical twilight, when the sky is dark enough to see faint stars. The glow of twilight is scattered sunlight, a gentle transition from day to night. It is light lingering in the sky, even after the source has vanished from view. Refraction in the atmosphere causes the sun to appear higher than it actually is. When you see the sun near the horizon, it is actually slightly below where it appears. Light from the sun bends as it passes through Earth's atmosphere, which is denser near the surface. This bending, or atmospheric refraction, lifts the image of the sun by about half a degree. This means you can see the sun even after it has technically set, and you see it rise before it has actually crossed the horizon. Refraction also flattens the appearance of the sun and moon near the horizon, making them look like ovals rather than circles. The atmosphere acts like a lens, bending light and altering what we see. Glories are colorful rings of light that appear around shadows in mist or clouds. If you have ever looked at your shadow on a cloud or mist from an airplane or mountaintop, you may have seen a glory, a series of colorful rings surrounding the shadow of your head. Glories are caused by light entering water droplets, scattering inside them, and exiting back toward the source. The process involves diffraction and interference, and the colors depend on the size of the droplets and the wavelength of light. Glories are closely related to rainbows, but they appear in the opposite direction. They are a beautiful and relatively rare phenomenon, a personal halo created by light and water. Halos around the sun and moon are caused by ice crystals in the atmosphere. Sometimes you can see a bright ring around the sun or moon. This is a halo, caused by light refracting through ice crystals in high-altitude clouds. The crystals are typically hexagonal, and light entering one face and exiting another bends by a specific angle, usually 22 degrees. This creates a ring of light at that angular distance from the sun or moon. Halos are different from coronas, which are caused by diffraction around water droplets and appear much closer to the light source. Halos are a sign of ice in the atmosphere, often a precursor to changing weather. They are beautiful and geometric, a demonstration of how crystals and light interact. Sundogs are bright spots that appear on either side of the sun. Sundogs, also called parhelia, are bright spots that appear to the left and right of the sun, often at the same altitude. They are caused by sunlight refracting through horizontally aligned ice crystals in the atmosphere. The crystals act like prisms, bending the light and creating two bright patches of light. Sundogs can be very colorful, with red on the side nearest the sun and blue on the outer side. They are often seen along with halos and are a sign of ice crystal clouds. Sundogs are striking and can be brighter than many stars, visible even in broad daylight. Light pillars are vertical columns of light caused by reflecting ice crystals. On cold nights, you might see what looks like a pillar of light extending upward from a streetlight or other bright source. This is a light pillar, caused by light reflecting off flat, horizontally floating ice crystals in the air. The crystals act like tiny mirrors, reflecting the light upward and creating a vertical column. Light pillars can also appear above the sun at sunrise or sunset. They are gentle and ethereal, a play of light and ice in the cold air. Crepuscular rays are beams of sunlight that appear to radiate from the sun. When the sun is low on the horizon and clouds block parts of it, you can see rays of light streaming through gaps. These are called crepuscular rays. They are actually parallel beams of sunlight, but perspective makes them appear to diverge from the sun. Dust, water droplets, and other particles in the air scatter the light, making the beams visible. Crepuscular rays are dramatic and beautiful, often seen at sunrise and sunset. They are sometimes called sun rays or God rays. They remind us that air is not empty, but filled with particles that interact with light. Anti-crepuscular rays appear to converge at the point opposite the sun. Anti-crepuscular rays are the continuation of crepuscular rays. They appear to converge at the antisolar point, the point in the sky directly opposite the sun. Like crepuscular rays, they are parallel beams of sunlight made visible by scattering. Perspective makes them appear to meet at a point on the opposite horizon. They are rare and require clear skies in the direction opposite the sun. Seeing them is a reminder of the geometry of light and the curvature of the sky. The green flash is a rare optical phenomenon seen at sunrise or sunset under very specific conditions. Just as the sun rises or sets, a brief flash of green light can appear at the top of the solar disk. This is called the green flash. It occurs because the atmosphere acts like a prism, refracting different colors by different amounts. As the sun sets, red light disappears first, then orange, yellow, and green, blue, and violet scatter away. For a moment, only green is visible. The effect lasts only a second or two and requires a clear, distant horizon and a stable atmosphere. The green flash is rare and beautiful, a fleeting gift of light and atmosphere. The blue hour is a period of twilight with a deep blue sky. The blue hour is the time shortly before sunrise or after sunset, when the sun is below the horizon and the sky takes on a deep, rich blue color. Indirect sunlight, scattered by the atmosphere, creates this even, soft light. Photographers prize the blue hour for its quality of light, which is diffuse and flattering. The exact timing and duration vary with latitude and season, but it is always a brief window. The blue hour is a transition, a quiet moment when day and night overlap. The golden hour is the time shortly after sunrise or before sunset when light is warm and soft. The golden hour is beloved by photographers and filmmakers. It occurs when the sun is low on the horizon and sunlight travels through more atmosphere. This filters out blue light and allows warm tones, reds, oranges, and yellows, to dominate. The light is also softer because it is less intense. Shadows are long and gentle. The quality of light during the golden hour is flattering and beautiful, casting a warm glow over everything. It is a time of day when light feels tangible and magical. Noon sun is the harshest light because it comes from directly overhead. When the sun is at its highest point in the sky, around noon, the light is intense and harsh. It casts short, sharp shadows and creates strong contrasts. This is because the light travels through the least amount of atmosphere, so little is scattered or absorbed. Colors appear washed out, and the light can be unflattering for photography and uncomfortable for the eyes. Noon light is powerful and direct, the sun at its strongest. The angle of sunlight affects how much energy reaches the surface. When sunlight hits the Earth at a steep angle, the energy is spread over a smaller area and is more intense. When it hits at a shallow angle, the energy is spread over a larger area and is weaker. This is why the equator is warmer than the poles. At the equator, sunlight strikes nearly perpendicular to the surface. At the poles, it arrives at a shallow angle, even at noon. The angle of sunlight also changes with the seasons. In summer, the sun is higher in the sky, delivering more energy. In winter, it is lower, delivering less. This variation drives the seasons and shapes climate. Solar eclipses happen because the moon blocks the sun's light. A solar eclipse occurs when the moon passes between the Earth and the sun, casting a shadow on Earth. If you are in the path of the moon's shadow, you see the sun partially or totally blocked. During a total solar eclipse, the moon exactly covers the sun's disk, revealing the sun's outer atmosphere, the corona, as a glowing halo. The sky darkens, stars appear, and the temperature drops. Total solar eclipses are rare at any given location and last only a few minutes. They are among the most dramatic natural events, a perfect alignment of sun, moon, and Earth. The corona of the sun is only visible during a total solar eclipse. The sun's outer atmosphere, called the corona, is incredibly hot, but also very faint. Normally, the bright light of the sun's surface overwhelms it, making it invisible. But during a total solar eclipse, the moon blocks the bright disk, and the corona becomes visible as a delicate, glowing halo. The corona extends millions of kilometers into space and has a temperature of millions of degrees, far hotter than the surface. Why it is so hot is a mystery that scientists are still trying to solve. Eclipses offer a rare opportunity to study the corona without specialized instruments. Diamond rings appear at the start and end of a total solar eclipse. Just before and after totality, when the moon almost completely covers the sun, a single bright point of sunlight can shine through a valley on the edge of the moon. Combined with the faint glow of the corona, this creates the appearance of a diamond ring in the sky. It is a fleeting moment of beauty, a signal that totality is about to begin or has just ended. The diamond ring effect is one of the most iconic sights of a solar eclipse. Lunar eclipses turn the moon red due to Earth's atmosphere. During a lunar eclipse, Earth passes between the sun and the moon, casting its shadow on the moon. The moon does not disappear. Instead, it often turns a deep red or orange. This is because Earth's atmosphere bends sunlight around the planet and into the shadow. The atmosphere filters out blue light and allows red light to pass through, bathing the moon in a reddish glow. The exact color depends on the amount of dust and clouds in Earth's atmosphere. After volcanic eruptions, lunar eclipses can appear especially dark and red. The moon has no atmosphere, so shadows there are very sharp. On the moon, there is no air to scatter light. This means shadows are stark and black, with no gradual transition. The sky is always black, even during the lunar day, because there is no atmosphere to scatter sunlight. Astronauts on the moon saw sharp contrasts, bright sunlit areas next to pitch-black shadows. The lack of atmosphere also means there is no diffusion of light, no softening. Everything is harsh and clear. The moon is a place where light behaves differently, unmediated by air. Planets reflect sunlight, which is why they are visible from Earth. Planets do not produce their own light. They shine by reflecting sunlight. The brightness of a planet depends on its size, distance from the sun, distance from Earth, and the reflectivity of its surface and atmosphere. Venus is the brightest planet because it is close, covered in highly reflective clouds, and often near Earth. Jupiter is also bright due to its large size. Mars appears reddish because its surface is covered in iron oxide, which reflects more red light. By observing the light reflected from planets, astronomers can learn about their composition, atmosphere, and surface. Exoplanets have been discovered by observing the dimming of distant stars. Most exoplanets are too faint to see directly. Instead, they are detected by the effect they have on their star's light. When a planet passes in front of a star, it blocks a tiny fraction of the star's light. This is called a transit. By carefully measuring the brightness of a star over time, astronomers can detect these tiny dips and infer the presence of a planet. The size of the dip tells you the size of the planet. The timing tells you the orbital period. Thousands of exoplanets have been discovered this way. Light, dimmed by a fraction of a percent, reveals worlds orbiting distant suns. Spectroscopy of exoplanet atmospheres reveals their composition. When an exoplanet transits its star, some of the star's light passes through the planet's atmosphere. Different gases absorb different wavelengths, leaving a signature in the spectrum of the light. By analyzing this spectrum, astronomers can determine what gases are present in the planet's atmosphere. Water vapor, methane, carbon dioxide, and other molecules have been detected this way. This technique, called transmission spectroscopy, allows us to study the atmospheres of planets light years away. Light carries not just an image, but a chemical fingerprint. The James Webb Space Telescope uses infrared light to see through dust. Visible light is absorbed by cosmic dust, making some regions of space opaque. But infrared light, with its longer wavelength, can penetrate dust clouds. The James Webb Space Telescope observes primarily in infrared, allowing it to see stars forming inside nebulae, galaxies hidden behind dust, and the most distant objects in the universe, whose light has been redshifted into the infrared. By observing in infrared, Webb reveals what is hidden in visible light, opening new windows on the cosmos. The Hubble Space Telescope captures images across ultraviolet, visible, and infrared. The Hubble Space Telescope has produced some of the most iconic images in astronomy. It observes in ultraviolet, visible, and near-infrared wavelengths. By combining images taken in different wavelengths, Hubble creates colorful, detailed pictures of nebulae, galaxies, and other objects. These images are not just beautiful. They reveal structure, composition, and processes invisible to the naked eye. Hubble has transformed our understanding of the universe, and its images have brought the cosmos into the public imagination. Radio telescopes observe the longest wavelengths of light. Radio telescopes detect radio waves, the longest wavelengths in the electromagnetic spectrum. They are large dishes that collect and focus radio waves onto a receiver. Because radio waves are so long, radio telescopes must be very large to achieve good resolution. Some, like the Arecibo Observatory before its collapse, were hundreds of meters across. Others, like the Very Large Array, combine signals from multiple dishes to create the equivalent of a much larger telescope. Radio telescopes have revealed pulsars, quasars, the cosmic microwave background, and the structure of galaxies. They observe a part of the spectrum invisible to optical telescopes, expanding our view of the universe. And so, dear listener, our journey through the wonders of light and color comes to a close. From the dual nature of photons to the bending of space by gravity, from the colors of rainbows to the invisible reach of ultraviolet and infrared, from the smallest particles to the largest structures in the cosmos, we have wandered together through a world built on light, shaped by light, and revealed by light. We have learned that light is not just what we see. It is a carrier of energy, a tool for measurement, a link to the past, and a window into the future. It is both wave and particle, both visible and invisible, both simple and endlessly complex. Light surrounds us, fills the universe, and connects us to the stars themselves. Every color we see, every shadow that falls, every glimmer and glow is a story told in light. As you lie here, letting your breath fall into an easy rhythm, imagine yourself surrounded by light. Picture sunlight streaming through a window, warm and golden. See the soft blue of the sky, the shimmer of water, the arc of a rainbow stretching across the horizon. Feel the invisible warmth of infrared, the hidden energy all around. See the stars above, their light traveling for years, centuries, eons, to reach your eyes. All of it is light. All of it is connected. The glow of a firefly, the flash of a distant supernova, the soft luminescence of the deep sea, the laser cutting through metal, the photon caught in a solar panel, the warm flicker of a candle. Light in all its forms, dancing through the universe, revealing the nature of reality itself. Just as light travels from source to observer, carrying information across the void, so too does your consciousness drift from waking to dreaming, from thought to stillness, from the bright noise of the day into the soft quiet of sleep. Let the light fade gently. Let the colors soften. Let the warmth wrap around you like a blanket. The universe is vast, ancient, and endlessly luminous, and you are part of it. resting under its glow, held by its light. Close your eyes, breathe deeply, and drift into the embrace of sleep, into stillness, into the vast and timeless quiet where all light converges and all journeys end. Good night.